Hello there, and welcome to Life Beyond Scene, where curiosity settles in, gets comfortable, and science takes the scenic route toward rest. Tonight, we're turning our attention to something that looks calm, familiar, even peaceful at first glance, yet holds a reputation that has unsettled sailors, swimmers, and entire towns for centuries. We're talking about the Great Lakes. 5 enormous bodies of fresh water sitting quietly between the United States and Canada, often photographed at sunset, often described as beautiful, and very often underestimated. If you've ever stood on the shore of one of them, you may have noticed something curious. The horizon stretches out so far that it looks like the ocean. The water meets the sky in a straight, distant line. Gulls circle overhead. The wind moves across the surface in long, steady motions. It feels expansive. It feels open. It feels, perhaps, harmless. And yet, these lakes have swallowed ships the size of apartment buildings. They generate storms that rival coastal systems. They claim lives every single year, often in circumstances that began with someone thinking, "It's just a lake." Before we go any further, I'd love to know where you're listening from tonight. Are you near water, landlocked? Is it late where you are, or still early? There's something fitting about discussing massive bodies of water while sitting safely wherever you happen to be, maybe under a blanket, maybe winding down from a long day. If you find this kind of slow, steady exploration relaxing, I'd be grateful if you gave the video a like, or perhaps subscribed. It helps this quiet corner reach others who enjoy learning without being rushed. Now, let's begin gently. The Great Lakes consist of 5 connected freshwater lakes: Superior, Michigan, Huron, Erie, and Ontario. Together, they hold about 20% of the world's surface freshwater supply. That number alone is difficult to picture. Imagine 1/5 of all the accessible freshwater on Earth gathered into 5 enormous basins. That's not a small regional feature. That's a system large enough to influence weather, shipping, ecosystems, and even international economies. Lake Superior alone is the largest freshwater lake by surface area in the world. It spans over 31,000 square miles. To put that into perspective, you could fit the entire state of South Carolina inside it and still have room to spare. It reaches depths of over 1,300 feet. If you were to drop the entire city of Chicago into its deepest point, many of the skyscrapers would disappear below the surface. But here's where the illusion begins. When most people hear the word lake, they picture something manageable, a place you can paddle across, a body of water that warms up in summer, a shoreline that feels contained. Lakes, in everyday language, are smaller than oceans. They feel safer. They feel contained by land, as though the surrounding geography keeps them in check. The Great Lakes do not behave like typical lakes. They behave like inland seas. The size alone changes the physics. Wind travelling across a small lake builds modest waves because it runs out of room. There isn't enough distance, what scientists call fetch, for energy to accumulate. On the Great Lakes, however, wind can travel uninterrupted for hundreds of miles. That distance allows waves to grow tall, steep, and powerful. Unlike ocean waves, which often have longer intervals between crests, Great Lakes waves are short-period waves. They come quickly, they stack tightly together. For boats, especially smaller ones, that means less time to recover between impacts. Instead of rising and falling in a slow rhythm, vessels can be hit repeatedly in rapid succession. This surprises people. Ocean waves look intimidating. Great Lakes waves often do not, at least not until they are already building. Then there is the matter of storms. Because the lakes are so large, they create their own weather patterns. Cold air moving over relatively warmer water in autumn can generate intense systems quickly. Storms can form with limited warning. Wind speeds increase, pressure drops, waves escalate. What began as a calm morning can turn into a dangerous afternoon. The scale of these lakes also affects temperature in ways that are not obvious. Fresh water behaves differently from salt water. It has a different density profile. It cools and warms at different rates. Even in summer, large portions of the Great Lakes remain dangerously cold below the surface. Surface temperatures might feel comfortable near shore, but only a few feet down the water can drop dramatically. Cold water presents a risk that many people underestimate. When someone falls into water below about 60 degrees Fahrenheit, cold shock can set in almost immediately. Breathing becomes involuntary and rapid. Muscles tighten. Coordination decreases. In water closer to 50 degrees, survival time can shrink quickly without proper protective gear. And because these are freshwater lakes, buoyancy is slightly reduced compared to saltwater. The difference is subtle, but it exists. Saltwater helps the human body float more easily due to its higher density. Freshwater does not provide quite the same lift. It's a small factor, but when combined with waves, wind, and cold, small factors add up. Distance is another quiet hazard. On a clear day, you can look across Lake Michigan and see nothing but blue. It looks crossable. It looks like something you could handle in a kayak, or even by swimming short stretches near shore. The problem is scale distortion. Without landmarks, humans are poor judges of distance across open water. What looks like a short paddle can be miles. What looks like a reachable sandbar can be much farther than expected. Fog adds another layer. The temperature differences between air and water frequently generate dense fog banks. Visibility can drop quickly. Boats lose visual reference points. Orientation becomes difficult. Even experienced navigators rely heavily on instruments in these conditions. And yet, for all of this, the lakes maintain a reputation as recreational spaces. Beaches line their shores, families swim, boats launch daily. Fishing is common. This normalcy reinforces the idea that the water is manageable. That perception is part of the danger. Humans tend to calibrate risk based on familiarity. Oceans feel wild because they are often portrayed that way. Lakes feel domestic. The Great Lakes sit in a category that confuses the brain. They look familiar but behave with ocean-scale power. History reinforces this reality. Over 6,000 documented shipwrecks lie beneath the Great Lakes. Some estimates suggest the number could be closer to 10,000. Many of these vessels were large cargo ships, carrying iron ore, coal, grain. Entire crews were lost in storms that escalated rapidly. One of the most famous examples is the sinking of the Edmund Fitzgerald in 1975 on Lake Superior. The ship was 729 feet long. It disappeared during a severe storm in November. All 29 crew members were lost. The scale of that vessel and its sudden disappearance changed how many people viewed the lakes. But even beyond large commercial ships, smaller craft encounter serious risk. Recreational boaters can be overwhelmed by steep waves. Kayakers can be pushed offshore by sudden wind shifts. Swimmers can be caught in structural currents near piers and breakwalls, which function similarly to ocean rip currents. These currents are not always visible from shore. Water flows outward through channels created by sandbars or man-made structures. A swimmer caught in one may feel as though they are being pulled directly away from land. Panic often worsens the situation. The safest response, swimming parallel to shore to escape the current's channel, is not intuitive when fear takes over. The lake's depth adds another quiet factor. Lake Superior contains enough water to cover all of North and South America under about a foot of water. That volume means energy storage. Wind energy transfers into wave energy. Temperature gradients influence air masses. The lakes are not passive basins. They are active systems. Seasonal changes also amplify risk. Autumn brings what locals sometimes call the Witch of November, a period known for particularly intense storms. Cold Arctic air collides with warmer lake water. Pressure systems deepen. Waves can reach over 25 feet in severe conditions. The timing often catches shipping vessels late in the season when traffic is still heavy. Winter introduces ice hazards. Ice sheets form, shift, crack and pile into pressure ridges. What looks like solid ground can fracture unexpectedly. People walking out onto frozen sections sometimes misjudge thickness. Ice rescues are complex and dangerous. Despite modern forecasting technology, unpredictability remains. Weather models have improved dramatically over the past decades. Satellite data, radar systems, buoy networks, and computer simulations all contribute to more accurate predictions. Even so, localized wind patterns and rapid pressure shifts can produce sudden changes. Rescue operations face additional complications due to the lake's size. When someone goes missing offshore, search areas are enormous. Cold water reduces survival windows. Waves and wind interfere with visibility and maneuverability. Timing becomes critical. There is also a psychological component worth considering. Standing on the shore of Lake Huron or Erie does not trigger the same instinctive caution as standing before the Atlantic. The word lake lowers defences. Familiar environments tend to feel safer. People may skip life jackets on short outings. They may ignore small craft advisories. They may swim farther than intended. The danger is not constant. Millions of people enjoy the Great Lakes safely every year. That is important to remember. The lakes are not malicious. They are not unpredictable at every moment. They simply operate according to physical laws that are easy to forget when the surface appears calm. Scale, temperature, wind, depth, and human perception intersect here in a way that can produce serious consequences when underestimated. If you were to look at a satellite image of the region, you would see what appears to be an inland ocean system. The lakes connect through straits and rivers. Water flows from Superior down to Ontario and eventually into the Atlantic Ocean through the St. Lawrence River. It is a dynamic chain. That connection means storms and water levels can influence each other across basins. Seaches, which are standing wave oscillations similar to water sloshing in a bathtub, can raise and lower water levels along shorelines dramatically within short periods. These oscillations have caused sudden flooding in certain coastal communities. Even atmospheric pressure alone can alter water height measurably. When pressure drops during storms, water can rise temporarily. Combined with wind-driven waves, that rise contributes to coastal erosion and structural damage. None of this requires dramatic storytelling. The physics is straightforward. Large surface area allows wind energy transfer. Cold fresh water reduces survival time. Depth stores thermal energy. Rapid weather shifts create steep waves. Human perception lags behind these realities, and so the question begins to shift slightly. It's not simply why the Great Lakes are dangerous, it's why they are perceived as less dangerous than they are. That perception gap is where most incidents begin. From here, it becomes useful to look more closely at how these lakes formed in the first place, because their origins explain much about their present behaviour. Their immense depth, their irregular shorelines, their varying basins, all trace back to events that unfolded thousands of years ago when glaciers covered much of North America, reshaping the land in ways that still influence wind, water, and weather patterns today. When most people think of danger at sea, they picture salt water stretching endlessly beyond the horizon, cargo ships rising and falling in long swells, perhaps a lighthouse blinking against a dark Atlantic sky. Very few picture fresh water framed by pine trees bordered by cities, dotted with sailboats and beach towels. And yet, the Great Lakes regularly produce conditions that mirror coastal oceans so closely that seasoned mariners often speak of them with the same respect they reserve for open sea. It is easy to forget just how large these lakes truly are. Lake Superior alone contains more water than the other 4 Great Lakes combined. Its surface area is so wide that in certain locations you cannot see land in any direction. On a clear day, standing on its southern shore, you're looking out across a stretch of water that extends more than 160 miles before reaching the opposite side. That distance is not visually obvious. The brain, trained by smaller lakes and ponds, struggles to scale what it sees. This is where the disguise begins. Fresh water, psychologically, feels gentler. The absence of salt, the lack of tidal charts in casual conversation, the word lake itself all contribute to a subtle downgrade in perceived risk. But water does not care about language. It responds to physics. One of the most important similarities between the Great Lakes and oceans is fetch, the uninterrupted distance over which wind blows across water. On small lakes, wind encounters shoreline quickly. The energy transfer is limited. On Lake Michigan, however, a strong north wind can travel nearly the entire length of the lake, over 300 miles, building wave height steadily along the way. By the time that wind-driven energy reaches the southern basin near Chicago or Indiana, it can produce waves that rival coastal storm surf. These waves are not gentle rollers. They are steep, tightly spaced, and forceful. Ocean waves often have longer periods between crests, sometimes 10 seconds or more. This spacing allows vessels to rise and fall in a more gradual rhythm. On the Great Lakes, wave periods are often much shorter, sometimes just 3 to 6 seconds during storms. That means boats encounter the next wave almost immediately after the last. For smaller craft, this creates a punishing motion. There is little time to recover balance or adjust heading. The bow may plunge into the next crest before lifting fully from the previous trough. Water can come over the deck quickly. Stability becomes harder to maintain. Commercial shipping captains have long recognized this distinction. Even large freighters, built specifically for Great Lakes transport, have reported severe strain during major storms. The combination of short-period waves and high wind speeds generates chaotic surface conditions. Unlike oceans, the Great Lakes do not have tides in the traditional sense. There is no twice-daily rise and fall driven by the gravitational pull of the moon and sun. This absence sometimes reinforces the perception that the lakes are simpler systems. But instead of tides, they experience seiches. A seiche is a standing wave oscillation that can cause water levels to shift dramatically along shorelines. Imagine pushing water from one end of a bathtub to the other. The water piles up at one side, then sloshes back. On the Great Lakes, strong sustained winds can push massive volumes of water toward one shoreline. When the wind subsides or shifts, that water surges back. These oscillations can raise or lower water levels by several feet in a matter of hours. For coastal communities and boaters, this can create unexpected conditions. Docks may suddenly sit higher above the waterline. Harbours may experience strong surges. In extreme cases, shoreline flooding can occur without traditional storm surge patterns seen on ocean coasts. Then there is the matter of storms themselves. The Great Lakes sit in a region where contrasting air masses frequently collide. Cold, dry air from Canada moves southward. Warm, moist air from the Gulf of Mexico moves northward. When these systems meet over the relatively warm lake surfaces, especially in autumn, powerful low-pressure systems can develop rapidly. Meteorologists sometimes refer to certain autumn storms as gales of November. Wind speeds can exceed 60 miles per hour. Waves can reach heights over 20 feet. Visibility can drop as rain, snow, or sleet moves in. Because the lakes are enclosed by land, storm systems can intensify in ways that surprise those unfamiliar with the region. The shape of the basins funnels wind. Shorelines can reflect and refract wave energy. Pressure gradients tighten quickly. It is not unusual for a calm morning forecast to shift toward advisory conditions by afternoon. Recreational boaters caught far from shore during such transitions can find themselves facing conditions far beyond their vessel's design limits. Distance compounds the risk. On oceans, mariners expect long travel distances. On lakes, shorter trips feel manageable. Someone launching from Milwaukee might plan to cross to Michigan's shoreline, a trip of roughly 80 miles. On a map, that may not look extreme, but once offshore, surrounded by water in all directions, the psychological effect changes. Without visible landmarks, orientation becomes more difficult. Fog can roll in quickly, especially when warm air passes over cooler water. Visibility can drop to near zero. Navigation then relies entirely on instruments. For smaller boats without advanced systems, this can be disorienting. Freshwater density also influences behaviour in subtle ways. Saltwater is denser than freshwater. That increased density provides slightly more buoyancy. In practical terms, objects and people float a bit more easily in ocean water. In freshwater, the human body sits slightly lower in the water, while the difference is modest. In cold, rough conditions, even small variations in buoyancy matter. Cold water deserves particular attention. The Great Lakes remain cold for much of the year. Because of their depth and volume, they warm slowly in spring and early summer. Even when surface temperatures reach comfortable levels near shore, deeper sections remain frigid. If someone falls overboard in water below 60 degrees Fahrenheit, cold shock can trigger involuntary gasping and rapid breathing. This immediate reaction increases the risk of inhaling water. Muscle function declines as body temperature drops. Swimming ability deteriorates quickly. In water closer to 50 degrees, exhaustion and unconsciousness can occur in less than an hour without protective gear. In even colder conditions, survival windows shrink further. Ocean swimmers often expect cold currents. Lake swimmers may not. Another ocean-like feature of the Great Lakes is structural current formation near piers and breakwalls. When waves approach a shoreline at an angle, water piles up along the beach. That water must return somewhere. It often channels back out through narrow pathways, forming rip currents. Many people associate rip currents exclusively with ocean beaches. However, they occur frequently along Great Lakes shorelines. The mechanics are the same. Water seeks balance. If waves continue pushing water toward land, a concentrated flow outward forms. These currents can be powerful enough to pull swimmers several hundred feet offshore. Panic is common. Swimmers instinctively try to fight directly against the current, expending energy and increasing exhaustion. The recommended response, swimming parallel to shore until free of the current's channel, requires calm decision-making that can be difficult under stress. Winter adds yet another layer to the disguise. When parts of the Great Lakes freeze, they can appear solid and stable. Ice sheets form along shorelines, snow accumulates, the surface looks walkable. However, ice thickness varies significantly depending on water movement, temperature fluctuations, and currents below. Wind can shift large ice sheets, causing pressure ridges to form. Cracks can open unexpectedly. Individuals venturing onto the ice sometimes underestimate these dynamics. Even in fully frozen conditions, sections near river mouths or deeper channels may remain thinner. Rescue operations in icy water are particularly hazardous due to rapid hypothermia onset. Despite all these parallels with ocean behaviour, one crucial difference stands out: cultural expectation. When people visit the Atlantic or Pacific, there is often an implicit understanding of risk. Lifeguards post flags indicating surf conditions. Warning signs reference rip currents and undertow. The language of caution is embedded in coastal tourism. Around the Great Lakes, the messaging can feel softer. Beaches are marketed as family-friendly. Shorelines are lined with homes, parks and boardwalks. The environment feels domestic. That sense of familiarity lowers psychological barriers. Statistics reflect this mismatch between perception and reality. Each year, dozens of drownings occur on the Great Lakes, many during conditions that were forecasted as hazardous. In numerous cases, individuals entered the water despite posted warnings. The danger is not constant, but it is conditional. When wind, temperature, and human behaviour align in certain ways, the lakes respond with force. Shipping history further reinforces their oceanic nature. More than 6,000 known shipwrecks rest beneath the Great Lakes. Some estimates suggest significantly more remain undiscovered. The cold fresh water slows the decay of wooden hulls compared to saltwater environments. As a result, wrecks often remain remarkably preserved. Divers exploring these wreck sites frequently describe them as time capsules. Entire vessels lie upright on the lake floor, masts intact, cargo still aboard. The scale of these ships underscores the seriousness of the conditions that sent them down. Large steel freighters have broken apart during storms. Smaller schooners have vanished without distress calls. In many cases, sudden weather escalation played a key role. Autumn, in particular, has earned a reputation for severe storms. When cold Canadian air sweeps across relatively warmer lake water, pressure systems deepen rapidly. The resulting gales can last for days. During such events, wave heights can exceed 25 feet. Combined with shortwave periods, these conditions create chaotic surface patterns. Even modern vessels equipped with advanced forecasting tools must plan carefully. The lakes also influence regional climate in ways similar to oceans. They moderate temperatures in surrounding areas. They generate lake-effect snow when cold air passes over warmer water, picking up moisture and depositing heavy snowfall downwind. Entire communities in western Michigan and upstate New York experience significant winter snowfall due to this process. This atmospheric interaction further demonstrates that the Great Lakes operate as large-scale environmental systems, not small recreational ponds. Sound behaves differently over large water surfaces as well. On calm days, sound can travel long distances across the lakes. Foghorns, boat engines, even distant waves can carry farther than expected. In heavy fog, this can create confusing acoustic illusions. A boat may sound closer or farther than it truly is. Navigation requires constant awareness of these sensory distortions. Modern technology helps mitigate many risks. Radar systems, GPS navigation, real-time weather data, and buoy networks provide valuable information. Commercial shipping lanes are monitored carefully. Still, technology does not eliminate physical forces. A vessel caught broadside to steep waves remains vulnerable. A swimmer caught in a rip current still faces strong outward flow. The lakes demand respect because they combine the power of ocean-scale physics with the subtle familiarity of inland geography. They are enclosed but not contained. They are freshwater but not gentle. They lack tides but not oscillations. They sit inland but behave at times like coastal seas. This dual identity is what makes them deceptive. A calm sunrise over Lake Huron can look indistinguishable from a tranquil bay. Hours later, the same water can be driven by wind into steep, crashing surf. The shift is not dramatic in the way hurricanes are dramatic. It is procedural. Wind builds, waves respond, temperature interacts, physics unfolds. Understanding this disguise requires shifting mental categories. The Great Lakes are not oversized ponds. They are inland seas governed by the same fundamental laws that shape oceans. Wind transfers energy across surface area. Pressure systems develop. Cold water extracts heat from the human body efficiently. Once that reclassification happens, the narrative changes. Safety practices align more closely with coastal standards. Life jackets become routine. Weather forecasts are checked with seriousness. From here, it becomes useful to look backward in time, to understand how something so vast and deep came to exist far from any coastline. The answer lies not in gentle accumulation, but in immense sheets of ice that once covered much of North America, carving basins that would eventually fill with fresh water on a scale few landscapes on Earth can match. Long before freighters crossed these waters, and long before beach towns lined the shorelines with boardwalks and marinas, the landscape looked nothing like it does today. There were no lakes here, no harbours, no lighthouses standing against grey horizons. Instead, much of North America lay buried beneath ice, not a thin seasonal coating, but ice thousands of feet thick, stretching as far as the eye could see. To understand why the Great Lakes are so vast, so deep, and in many ways so ocean-like, it helps to begin there, in a world shaped not by waves, but by glaciers. Around 20,000 years ago, during the last ice age, enormous ice sheets covered much of what is now Canada and the northern United States. The Laurentide ice sheet, one of the largest, extended southward across the Great Lakes region. In some places it was more than a mile thick. Imagine standing beneath a ceiling of ice taller than most skyscrapers, pressing down with unimaginable weight. Ice at that scale does not simply sit still, it moves, slowly, almost imperceptibly over human timescales, but steadily. Glaciers behave like extremely thick rivers. Under pressure, ice deforms and flows outward from its centre of mass. As it moves, it grinds against the land beneath it. Rock is scraped, soil is bulldozed, entire layers of earth are carved away. This is not a gentle process. The advancing and retreating glaciers acted like massive sculpting tools, deepening valleys and gouging out basins. The Great Lakes sit within some of these carved depressions. Over thousands of years, repeated glacial advances and retreats widened and deepened these low areas. The weight of the ice also pressed the Earth's crust downward. Land that had once sat higher was forced lower under the immense load. When the glaciers eventually began to melt and retreat northward, the depressions they left behind filled with meltwater. The ice sheets withdrew, but the basins remained. That is how the lakes were born. Lake Superior in particular occupies a basin carved deeply into ancient bedrock. Its depth is not simply a surface feature. It is the result of repeated glacial scouring and tectonic structures that predate even the Ice Age. Beneath its waters lie some of the oldest exposed rocks on the planet, part of the Canadian Shield, formed billions of years ago. The glaciers did not create the bedrock itself, but they exposed and shaped it. As the ice retreated, meltwater pooled in the lowest areas. Channels formed between basins. Over time, water began flowing from the highest lake, Superior, down through connecting rivers and straits toward the Atlantic Ocean. What remains today is a chain of freshwater inland seas linked by gravity. The depth created by glacial carving is one of the key reasons the Great Lakes behave as they do. Deep water stores cold. It absorbs and retains thermal energy differently from shallow systems. Even in summer, large portions of the lakes remain cold far below the surface. This vertical temperature structure affects everything from weather patterns to human survival times. During spring, surface water begins to warm under increasing sunlight. However, the deeper layers remain cold. This creates stratification, a layering effect where warmer water sits above colder, denser water. Because fresh water reaches maximum density at about 39 degrees Fahrenheit, it behaves in a somewhat unusual way compared to other substances. As autumn arrives and surface water cools again, temperatures throughout the lake equalize. This process, known as turnover, allows water from different depths to mix. Nutrients are redistributed, oxygen levels shift. The entire system breathes, in a sense, on a seasonal rhythm. This seasonal mixing contributes to the lake's ability to generate powerful storms in fall. When cold air sweeps across relatively warm water, heat transfers upward into the atmosphere. That energy fuels low-pressure systems. Wind speeds increase, waves build. The depth carved by ice thousands of years ago directly influences storm intensity today. Glacial retreat also left behind irregular shorelines. Moraines, ridges of debris deposited by glaciers, form bluffs and dunes along many parts of the lakes. Underwater, the lake floors are not flat. They contain ridges, drop-off, submerged valleys and rock formations. These features influence wave behaviour and current formation. When wind-driven waves encounter uneven bottom topography, their energy can refract, focusing in certain areas. This can amplify wave height locally. Currents can accelerate through narrow underwater channels. Swimmers near piers or sandbars may encounter stronger flows because of how water interacts with these submerged contours. None of this is visible from the surface. Standing at the water's edge, you see blue stretching outward. Beneath that surface lies a complex landscape shaped by ice and gravity over millennia. The glaciers also left behind vast deposits of sediment. Sand beaches along Lake Michigan and Lake Huron owe their existence to glacial outwash and erosion. These beaches feel inviting. They resemble ocean shorelines. In many cases, they are nearly indistinguishable at a glance. But because there are no tides to regularly redistribute sediment in the same way as coastal systems, sandbars can form and shift in unpredictable patterns. Shallow areas may extend farther from shore than expected, followed suddenly by deeper troughs. When waves break over sandbars, water accumulates between the bar and the shoreline. That water must escape somewhere. Often it funnels outward through narrow gaps, forming rip currents. The underwater topography left behind by glaciers sets the stage for these flows. Patience was part of the process. The lakes did not appear overnight when the glaciers melted. The retreat of ice was gradual. As the ice sheet withdrew northward, proglacial lakes formed temporarily at different elevations. Some drained catastrophically when natural ice dams broke. Others shifted as land rebounded. Isostatic rebound continues even today. When the immense weight of the ice was removed, the Earth's crust began slowly rising back toward its original elevation. This rebound is uneven. Northern shores of some lakes are still rising slightly, while southern shores may experience relative lowering. Over thousands of years, this gradual adjustment alters shoreline contours and water flow patterns. The lakes are not static basins frozen in time. They are evolving systems. Lake levels fluctuate due to precipitation, evaporation, runoff, and long-term climatic cycles. Because of their enormous volume, these changes are often measured in inches or feet, rather than dramatic tidal swings. Still, even modest changes can affect coastal erosion and infrastructure. The sheer size of the basins means wind energy has room to develop fully. A small lake cannot support the same wave growth because its fetch is limited. But when glaciers carved hundreds of miles of open water space, they unintentionally set up the conditions for modern storm dynamics. It is a quiet chain of cause and effect. Ice flows, basins deepen, water fills them, wind crosses the surface, waves respond, storms build, ships encounter steep seas, swimmers face cold water. The timeline stretches across tens of thousands of years, but the consequences are immediate. The patience of geological processes contrasts sharply with the speed of human decision-making. A boater may decide to venture out based on a calm morning forecast. A swimmer may enter the water because it appears manageable. Neither may be thinking about glacial history. Yet that history determines the depth beneath them, the temperature below the surface, and the way waves will behave if wind increases. Lake Superior's average depth is nearly 500 feet. Its maximum depth exceeds 1,300 feet. That depth stores cold water even through warm summers. It allows large wave systems to propagate without interruption from shallow bottom friction. Lake Michigan and Lake Huron, connected by the Straits of Mackinac, function hydrologically as a single body of water. Together, they contain immense volume. Their elongated north-south orientation allows winds from certain directions to build waves over long distances. Lake Erie is shallower on average, with a maximum depth of about 210 feet. Its shallowness makes it warm more quickly in summer, but it also allows storms to churn its entire water column more easily. This can produce chaotic wave patterns and rapid changes in surface conditions. Lake Ontario, though smaller in surface area than some of the others, is still deep, reaching over 800 feet. Its proximity to the Atlantic via the St. Lawrence River integrates it into larger shipping networks. Each basin reflects glacial sculpting in slightly different ways. Depth, shape, orientation, and shoreline contour all influence how each lake behaves during changing weather. The Great Lakes are sometimes described as young in geological terms. They have existed in roughly their current form for about 10,000 years, a brief period compared to the age of the Earth. But that youth does not diminish their scale. If anything, their relative youth contributes to ongoing change. Shorelines continue to erode. Sand dunes migrate slowly. River inflows deposit sediment. Storm cycles reshape beaches. The patience of ice carved out a landscape that appears calm. Water filled it quietly. Over centuries, humans built cities along its edges. Ports developed, trade routes expanded, beach culture grew. But beneath the familiarity lies a structure created by forces far larger than human memory. When wind begins to move across Lake Superior in late autumn, it is interacting with a basin shaped by glacial mass. When waves rise along the eastern shore of Lake Michigan, they are rising over a floor carved by ice sheets. When cold water extracts heat from a swimmer's body, that temperature profile exists because of the lake's depth and volume. Ice did not intend danger, it shaped terrain. Yet the terrain it left behind enables the lake's ocean-like power. Even the clarity of the water in certain areas is influenced by glacial origin. The absence of salt reduces corrosion and changes biological composition. Cold temperatures slow decomposition. Shipwrecks remain preserved in ways they would not in saltwater oceans. Divers exploring these wrecks often describe the experience as surreal. Entire hulls lie intact on the lakebed, preserved by cold fresh water. The same cold that preserves history also reduces survival time for anyone unexpectedly immersed. It is a subtle duality. The lakes owe their existence to ice and patience. Their hazards arise from scale and physics. Standing at the edge of Lake Huron on a quiet evening, you might see nothing that hints at glaciers or ancient ice sheets. You see only a broad horizon and gentle waves touching sand. The history is invisible, but it is there in the depth beneath your feet, in the contours that guide currents, in the cold that lingers below the surface long after summer has arrived. The story of the Great Lakes begins not with storms, but with ice pressing downward over thousands of years, shaping basins large enough to mimic oceans. From that foundation, modern weather systems, wave patterns, and human encounters unfold. And once those basins were carved and filled, another layer of illusion settled in. Water, when calm, reflects the sky so perfectly that it appears flat and harmless. The surface can resemble polished glass. It is this stillness, especially on clear days, that often convinces people the system beneath is simpler than it truly is. There are mornings on the Great Lakes when the surface looks almost perfectly flat. The horizon forms a clean line. The water reflects the sky so evenly that it becomes difficult to tell where one ends and the other begins. Boats sit quietly in marinas. Gulls drift without urgency. From shore, it can feel as though nothing unpredictable could possibly happen in a place that looks so composed. That visual calm is one of the most convincing illusions these lakes produce. Water, when undisturbed, communicates safety. Humans are wired to interpret smooth surfaces as stable conditions. A still pond suggests control. A glassy bay suggests ease. When we see ripples instead of crashing surf, our internal warning systems remain quiet. But the Great Lakes are not defined by what they look like in a single moment. They are defined by how quickly that moment can change. Wind is the first factor in unravelling the illusion. Wind does not need hours to build waves on a system this large. Because the lakes offer such long uninterrupted distances, even a moderate increase in wind speed can begin transferring energy into the water almost immediately. A breeze at 10 miles per hour may only produce small ripples. At 20 miles per hour, wave formation becomes noticeable. At 30 or 40, the surface begins organising into steep, tightly spaced crests. What makes the transition deceptive is the delay between wind onset and shoreline impact. If you're standing near the southern end of Lake Michigan, and a strong north wind begins building waves 150 miles away, you may not feel the effects immediately. The energy is developing far upwind. Hours later, that accumulated force arrives at your shoreline in the form of larger surf. The sky above you may still appear partly clear. The shift feels sudden, but the process began much earlier. This time lag between cause and visible effect contributes to misjudgment. Boaters launching under relatively calm conditions sometimes fail to consider what wind patterns are developing across the entire basin. Because the lakes are so wide, weather at one end can differ significantly from the other. A calm harbour does not guarantee calm open water. Then there is atmospheric pressure. When pressure drops rapidly ahead of a storm system, wind speeds often increase. On large bodies of water, these pressure gradients can generate sustained winds that last for hours or even days. Waves grow not just in height but in complexity. They reflect off shorelines. They intersect at angles. They form irregular patterns. From a distance, a wave face may not look intimidating. But the steepness matters more than the height alone. On the Great Lakes, wave periods are often short. Crests follow one another quickly. The water between them does not have time to flatten out fully. For small boats, this creates a constant cycle of lifting and dropping, sometimes violently. The bow may climb sharply only to plunge into the trough ahead. Spray reduces visibility. Water accumulates on deck. To someone observing from shore, especially at a distance, the scene may still look manageable. Waves on fresh water do not always produce the same deep blue walls associated with oceans. They can appear smaller in scale, but their spacing and steepness amplify their impact. Stillness is also misleading beneath the surface. On calm days, swimmers often venture farther from shore because the water feels predictable. What is not visible is the presence of structural currents and longshore currents shaped by underwater contours. When waves approach a beach at an angle, they push water diagonally along the shoreline. This creates a current parallel to the beach known as a longshore current. Swimmers caught in it may find themselves drifting sideways without realizing how far they have moved. At the same time, water accumulating near shore must return outward. It frequently does so through narrow channels between sandbars, forming rip currents. These flows can exist even when wave height seems modest. A beach that appears placid from a distance may have strong outward-moving water in specific sections. The illusion deepens during temperature transitions. On hot summer days, the surface water near shore can warm significantly. It feels comfortable. Swimmers acclimate quickly, but only a few yards offshore, or a few feet below the surface, the temperature can drop sharply due to stratification. Sudden immersion into colder water can trigger gasping reflexes and muscle constriction. Someone diving from a boat may experience immediate breath disruption. If they were not expecting the cold, panic can set in. Again, nothing about the surface appearance signals this hazard. Fog introduces another layer of false security. Morning fog over the Great Lakes can look serene. It softens the horizon, it muffles sound. For kayakers or paddleboarders, it may even feel peaceful, but fog reduces spatial awareness. Landmarks disappear, distances become distorted. Without clear visual reference points, even experienced boaters can misjudge direction. Sound travels unpredictably over water, sometimes seeming closer or farther than it truly is. A distant engine may echo across the surface. Orientation becomes dependent on instruments. In such conditions, stillness is sensory rather than structural. The water may be calm, but navigation risk increases. Autumn brings one of the most striking examples of deceptive calm. Before major November storms, there are often periods of relative quiet. The air cools. The sky may even clear temporarily. Barometers drop steadily. But unless someone is watching readings carefully, that change is invisible. Then, as pressure systems intensify, wind accelerates, waves respond. What felt stable hours earlier transforms into aggressive surf. The speed of escalation matters. Large ocean storms are often tracked days in advance with significant media coverage. While forecasting on the Great Lakes has improved dramatically, localized intensification can still surprise those who rely solely on surface appearance. Human perception tends to prioritize what is immediately visible. If the water looks manageable, we assume it will remain so for at least the near future. But physics operates continuously, not episodically. Even during calm periods, the lakes are storing potential energy. Thermal differences between air and water accumulate. Wind patterns build elsewhere. Atmospheric systems move across continents. By the time visible change reaches a particular shoreline, the system has already been evolving. There is also the matter of scale distortion. Standing at the water's edge, It is difficult to comprehend distances of 50 or 100 miles across open water. The opposite shore is often invisible. Without that reference, the brain compresses scale. The surface looks closer than it is. This distortion influences decision-making. A paddler may believe they can handle conditions because the water looks contained. A swimmer may assume they are near shore because land remains visible behind them, not realizing how far they have drifted laterally. Even experienced individuals can misinterpret stillness. Commercial shipping captains monitor forecasts carefully because they understand how quickly conditions can shift. Smaller recreational boaters, however, may not carry the same tools or habits. A sunny morning launch can turn into a difficult return if wind increases from a different direction. One of the more subtle aspects of the illusion is sound. Calm water reflects and carries sound efficiently. Voices travel, distant waves echo faintly. This acoustic smoothness reinforces the feeling of quiet stability. When wind rises, the soundscape changes abruptly. Waves slap hulls, spray hits metal, engines strain against chop. The shift can feel dramatic precisely because the calm was so convincing. The lakes do not provide dramatic warning sirens. There is no visible boundary between safe and unsafe. Conditions transition gradually until they reach a threshold where recovery becomes difficult. Cold water compounds the illusion further. On warm days, swimmers may feel confident because the air temperature is high. Heat on the skin reduces awareness of underlying water temperature. Once submerged fully, the difference becomes clear. In fresh water, the body loses heat rapidly. Without protective suits, endurance is limited. The calm surface does not communicate this risk. There are days when waves are minimal but currents remain strong due to previous wind patterns. Even after a storm subsides, residual energy can linger in the water column. Swimmers entering what appears to be post-storm calm may encounter unexpected movement beneath the surface. Similarly, boaters heading out after visible whitecaps have diminished may underestimate how residual swell interacts with new wind directions. The lakes reward attentiveness rather than assumption. Lifeguards along certain Great Lakes beaches use coloured flag systems to indicate conditions. Red flags signal high hazard. Yellow flags suggest moderate risk. Green flags indicate low risk. These systems exist because visual inspection alone is not reliable. Rip currents are often invisible from eye level. They may only be detectable from elevated vantage points where subtle changes in watercolour or surface texture become visible. From standing height at the shoreline, the surface may appear uniformly calm. The illusion of stillness is therefore not an accident. It is a byproduct of how light interacts with water and how human perception prioritises surface cues over underlying forces. On many evenings, the lakes return to quiet. Sunset flattens wave faces. Wind subsides. Harbours become reflective again. In those moments, it can feel as though the earlier intensity never existed. But the forces remain. Depth remains. Temperature gradients remain. Underwater topography remains. Wind will return, driven by atmospheric patterns larger than the basin itself. Recognizing the illusion does not mean fearing the lakes constantly. It means adjusting expectations. A calm surface is a snapshot, not a guarantee. A quiet morning is an interval, not a promise. The Great Lakes, shaped by ice and governed by physics, move between states without emotional attachment. From here, the focus shifts naturally toward the systems that most dramatically break that stillness. The storms that rise quickly, sometimes without the kind of extended build-up people expect, and the way wind and pressure combine across such vast freshwater expanses to transform reflection into force. There is a particular kind of quiet that sometimes settles over the Great Lakes before a storm arrives. The air feels heavier. The horizon may blur slightly. Wind softens for a moment, as though the system is pausing. If you were standing on the shoreline without access to weather data, you might interpret that stillness as stability. It isn't. Storms on the Great Lakes do not always announce themselves in dramatic fashion. They often build from atmospheric conditions already in motion far beyond the visible skyline. By the time the change becomes obvious at water level, the machinery driving it has been assembling for hours, sometimes days. The geography of the region plays a crucial role. The Great Lakes sit in a corridor where major air masses frequently collide. Cold, dry air from northern Canada pushes southward. Warm, moist air from the Gulf of Mexico moves north. When these contrasting systems meet over large freshwater basins, the temperature difference can fuel rapid cyclonic development. Water holds heat differently than land. In autumn especially, the lakes remain relatively warm compared to the cooling air above them. When cold air sweeps across that warmer surface, heat transfers upward. Rising warm air lowers surface pressure. As pressure drops, surrounding air rushes inward. Wind accelerates. This process can intensify quickly. On smaller lakes, wind builds waves but does not necessarily alter broader weather patterns significantly. On the Great Lakes, the sheer surface area allows sustained heat exchange with the atmosphere. Storm systems can deepen while directly interacting with the water. This is why some of the most powerful storms in the region occur in late fall. By November, surrounding land has cooled considerably. The lakes, however, still retain stored summer warmth in their depths. That contrast sharpens the energy gradient. When strong low-pressure systems track across the basin, they can intensify dramatically. Wind speeds exceeding 50 or 60 miles per hour are not uncommon during severe autumn gales. Waves respond accordingly. On Lake Superior and Lake Michigan, wave heights can exceed 20 feet in strong systems. The short period between crests makes these waves especially forceful. Unlike tropical hurricanes, which attract days in advance and often covered extensively in national media, Great Lakes storms sometimes receive less attention outside the region. They are not categorized with dramatic names. They do not spiral visibly in satellite images with the same iconic symmetry, yet their local impact can be severe. One of the defining characteristics of these storms is speed of escalation. A low-pressure system moving eastward across the upper Midwest can intensify as it reaches the lakes. Pressure gradients tighten, wind fields expand, rain or snow begins falling in sheets, visibility drops. Within hours, previously calm water becomes chaotic. Boaters caught offshore during such transitions often describe the shift as abrupt, even when forecasts had indicated increasing winds. The psychological effect of watching conditions deteriorate in real time amplifies the sense of surprise. The lake's orientation also influences storm behavior. Lake Michigan and Lake Huron are elongated north to south. A strong north wind can travel the entire length of the basin, building wave energy over hundreds of miles. By the time it reaches southern shorelines, that energy manifests as powerful surf. Lake Erie, shallower and oriented more east to west, reacts differently. Its limited depth allows storms to stir the entire water column more easily. Waves may not reach the same towering heights as those on Superior, but they can become extremely steep and closely spaced. Lake Ontario, positioned downstream in the system, experiences storms influenced both by regional weather patterns and by water flow from upstream basins. Storm tracks vary. Some systems move west to east, others descend from the northwest. In winter, clipper systems bring sharp bursts of wind and snow. In spring, rapidly developing thunderstorms can sweep across open water with little warning. Lightning adds another layer of hazard. Open water offers no natural shelter. Boats become the highest points in a flat landscape. Thunderstorms forming over the lakes can produce strong downdrafts and sudden wind shifts known as gust fronts. These outflows can flatten sails and overturn smaller craft. In summer, warm, humid air passing over cooler lake water can create instability. Convective storms may form along boundaries where temperature differences are greatest. Radar may detect these developments, but from the water's surface, the sky may appear only mildly unsettled until the first gust hits. This unpredictability is not due to chaos in the scientific sense. It is the result of complex interactions between air, water, and land. Wind direction changes matter. If a strong offshore wind shifts suddenly onshore, wave direction reverses relative to the shoreline. Harbours that were sheltered moments earlier may become exposed. Boats anchored based on previous wind orientation may find themselves broadside to incoming waves. Pressure falls also influence water levels directly. As atmospheric pressure decreases, the weight of air pressing down on the lake surface lessens slightly. Water can rise incrementally in response. Combined with sustained wind pushing water towards certain shorelines, this can create temporary surges. Seiches often accompany strong storms. As wind piles water toward one end of a lake, levels rise there and drop at the opposite end. When the wind relaxes or changes, water sloshes back across the basin. These oscillations can last for hours or even days after the main storm passes. Communities along affected shorelines sometimes experience sudden water level changes without active rainfall at that moment. Docks may be submerged or left dry depending on the oscillation phase. Commercial shipping accounts for these risks carefully. Large freighters operating on the Great Lakes monitor barometric pressure and wind forecasts continuously. Even so, storms have historically overwhelmed vessels. The sinking of large ships during November gales serves as a reminder that size alone does not guarantee safety. Steel hulls have broken under wave stress. Cargo has shifted. Communication has been lost. For smaller recreational boaters, the margin for error is narrower. A forecast predicting winds increasing from 10 to 25 miles per hour may not sound extreme to someone accustomed to mild breezes. But on a basin with long fetch, that increase can generate significantly larger waves than expected. Human reaction time also plays a role. Once whitecaps begin forming consistently, returning to shore may already be more difficult. Waves build progressively. The earlier a boat turns back, the easier the return. Waiting until conditions appear clearly hazardous reduces options. Storms also alter water temperature profiles. Strong winds can disrupt stratification, mixing colder water upward. This can drop surface temperatures rapidly in localized areas. Swimmers and divers may encounter colder conditions than anticipated. Rainfall during storms increases runoff from surrounding land. Debris may enter the water. Visibility below the surface declines. Navigation hazards increase. The lake's vastness means help is not always immediate. Search and rescue operations operate efficiently in the region, but response times depend on distance and weather conditions. In heavy seas, aircraft and rescue vessels face their own limitations. From a shoreline perspective, storms can appear dramatic but distant. Observers watch waves crash against breakwalls and feel wind whipping across beaches. For those offshore, the experience is far more intense. There are also smaller-scale wind events known as squalls. These brief but powerful bursts of wind can form along frontal boundaries or ahead of larger systems. They may last only minutes but carry enough force to knock down masts or capsize small boats. Because squalls are localized, they can catch individual boaters unaware even when regional forecasts do not indicate sustained severe weather. Lake effect storms illustrate another dimension of rapid development. When cold air passes over warmer water, moisture evaporates and rises. As the air moves inland and cools further, it condenses into heavy snowfall. This process can produce intense snow bands downwind of the lakes, often in narrow corridors. For mariners still operating late in the season, lake effect snow reduces visibility dramatically. Navigation becomes difficult. Ice accumulation on decks and superstructures adds weight and destabilizes vessels. In winter, storms bring freezing spray. When waves crash against hulls in sub-freezing air, water droplets freeze upon contact. Ice builds up on railings, antennas, and rigging. Over time, this accumulation increases top weight and alters vessel balance. The lakes, though fresh water, generate maritime hazards indistinguishable in severity from oceanic conditions under the right circumstances. It is worth emphasizing that storms do not appear randomly. Meteorological science has advanced significantly. Forecast models track low-pressure systems with increasing accuracy. Marine advisories and gale warnings are issued regularly. The phrase, "rise without permission," reflects human perception more than atmospheric mystery. Storms do not ask whether anyone is ready. They follow gradients of temperature and pressure. They respond to jet stream positioning. They intensify when conditions align. From a calm shoreline, that progression may feel sudden. From a satellite view, it is procedural. Recognizing this helps recalibrate expectations. Checking forecasts specific to open water rather than relying solely on coastal conditions becomes essential. Understanding that wind elsewhere on the basin influences your location, hours later changes planning decisions. The lakes are dynamic because they are large enough to host full-scale weather interactions. Smaller lakes absorb storms differently. Oceans dissipate energy over even greater distances. The Great Lakes sit in a middle ground, enclosed yet expansive. They gather energy quickly and release it across contained boundaries. Standing at the water's edge during the early stages of a developing storm, you may feel only a slight shift in air temperature and a subtle strengthening of breeze. It rarely begins with chaos. Then gradually whitecaps multiply. Waves gain height. The surface texture roughens. Sound intensifies. Spray moves sideways rather than upward. Within hours, the illusion of stillness has vanished completely. Understanding these patterns does not remove the lake's power. It reframes it. From here, attention naturally turns to what happens once storms have built waves across such vast expanses, and why those waves, unlike many ocean swells, behave in ways that challenge even experienced sailors and swimmers alike. When most people imagine large waves, they picture ocean swells rolling in long, steady intervals. There is a rhythm to coastal surf that feels almost predictable. A crest rises, travels, breaks, and then there is a pause before the next one arrives. Even when the waves are large, there is often space between them, a breathing pattern that allows boats to rise and settle in sequence. The Great Lakes do not always offer that rhythm. Their waves are governed by the same physical principles as ocean waves, but the conditions under which they form are different enough to produce behaviour that surprises even experienced mariners. The first difference lies in fetch and confinement. On an ocean, wind may blow across thousands of miles of open water. Waves grow, but they also spread out over vast distances. Energy disperses in multiple directions. The scale is immense. On the Great Lakes, wind can travel uninterrupted for hundreds of miles, which is enough to build significant wave height, but the basin itself is enclosed by land. When strong winds push water toward one shoreline, that energy does not simply dissipate into endless space, it reflects. Reflected waves interact with incoming waves. Imagine two sets of ripples colliding in a bathtub. The peaks intersect, the troughs combine. Sometimes they cancel each other out, other times they amplify one another. On a basin as large as Lake Superior or Lake Michigan, this interaction occurs across miles of open water. The result is confused seas. Instead of orderly, evenly spaced swells, the surface becomes irregular. Waves approach from slightly different angles. Their crests intersect. Heights vary unpredictably. A vessel may climb one wave only to meet another at an angle it did not anticipate. This is where the phrase "don't follow the rules" begins to make sense. Mariners trained in ocean navigation often expect certain wave behaviours based on wind direction and fetch length. On the Great Lakes, those expectations can be disrupted by the basin's geometry. Short wave periods are a defining feature. In ocean storms, waves often have periods of 8 to 15 seconds or more between crests. On the Great Lakes, storm-driven waves frequently have periods of 3 to 6 seconds. That means the time between one crest and the next is much shorter. For a boat, this creates a different motion pattern. With longer periods, a vessel has time to rise with the wave and settle before the next arrives. With short periods, the bow may barely crest one wave before encountering another. the motion becomes sharp and repetitive. This repeated impact places stress on hulls, it increases fatigue for crews, it raises the risk of cargo shifting in larger ships and water coming aboard in smaller ones. The steepness of the waves compounds the issue. Wave steepness is determined by the ratio of wave height to wavelength. On the Great Lakes, because wavelengths are shorter, waves can be steeper for a given height. A 10-foot wave on Lake Erie may feel more abrupt than a 10-foot swell on the Atlantic. Steep waves break differently. They tend to crest sharply and collapse forward with force. Boats attempting to cut through them head-on may find themselves slamming into vertical faces of water. Approaching at an angle can reduce impact but introduces rolling motion. For small recreational boats, these dynamics can become overwhelming quickly. Kayaks and paddleboards face particular risk in building chop. The tight spacing between waves reduces stability. Recovery time after one crest is minimal before the next arrives. Even large freighters, designed specifically for Great Lakes conditions, have encountered structural stress during severe storms. The bending forces exerted along the length of a ship increase when waves lift the bow and stern simultaneously, while the midsection hangs in a trough. This phenomenon, known as hogging and sagging, is not unique to freshwater, but the short, steep nature of Great Lakes waves can intensify these stresses. Another factor that complicates wave behaviour is underwater topography. The lake floor is not uniform. Glacial carving left ridges, drop-offs and submerged valleys. When waves move from deeper water into shallower areas near shore, their speed decreases due to bottom friction. However, their energy remains. As wave speed decreases, height increases, the wave steepens, eventually it breaks. Because the bottom contours vary irregularly, waves may refract, bending towards certain areas. This can concentrate energy along particular stretches of shoreline. One section of beach may experience significantly larger breaking waves than another nearby section under the same wind conditions. To an observer walking along the shore, the variation may seem inconsistent. Structural features such as piers and breakwalls further altered wave patterns. When waves strike these structures, they reflect outward. Incoming waves then collide with reflected ones. This interaction creates standing waves and unpredictable surges. Swimmers near piers can be caught in powerful currents generated by these collisions. During storms, water can surge over breakwalls with surprising force. People standing on these structures to watch waves sometimes underestimate the power of a single larger crest. Rogue waves, or unusually large waves appearing among smaller ones, have also been documented on the Great Lakes. While not as dramatic as some oceanic rogue wave events, these larger crests result from wave interference. When multiple wave trains align constructively, their heights combine temporarily. A boat navigating what appears to be a series of moderate waves may suddenly encounter a crest significantly taller than the rest. Because wave periods are short, the window for adjustment is brief. Wind shifts add yet another layer. If wind direction changes during a storm, new wave sets begin forming while older ones continue propagating across the basin. The surface becomes a mix of wave directions. This cross-sea condition increases unpredictability. Ocean mariners often refer to cross seas as uncomfortable and challenging. On the Great Lakes, they can develop quickly due to the enclosed nature of the basin and the way wind interacts with shoreline boundaries. Then there is the matter of sea cheese interacting with wind-driven waves. As water oscillates back and forth across the lake due to previous wind forcing, new wind patterns can amplify or dampen certain oscillations. Water levels at one end of the basin may be temporarily elevated. Waves riding on top of that elevated surface gain additional height relative to structures and shorelines. In practical terms, this can mean waves overtopping breakwalls or docks that would normally remain dry. Ice conditions in winter alter wave behaviour again. When partial ice cover exists, open water areas between ice sheets can experience wave growth. These waves then impact ice edges, causing breakage and movement. The interaction between waves and shifting ice creates chaotic surface conditions. In early spring, when ice begins melting unevenly, large chunks can float offshore. Waves push them unpredictably. Boats navigating through such conditions must account for both water motion and solid obstacles. Sound and visibility distortions during storms further complicate perception of wave size. Spray reduces contrast. The horizon disappears. Without clear reference points, estimating wave height becomes difficult. A crest that looks manageable from a distance may appear far more imposing when approached. Fatigue also influences judgment. Repeated impact over shortwave periods exhausts crews. Reaction times slow. Decisions become less precise. This human factor combines with physical wave behaviour to increase risk. Despite all this, it is important to recognise that the waves themselves are not erratic in a mystical sense. They follow physical laws precisely. Energy transfers from wind to water. Depth influences speed. Interference patterns produce constructive and destructive interactions. The unpredictability arises from the complexity of multiple forces operating simultaneously in a confined yet expansive basin. For swimmers, the primary concern is not wave height alone, but the currents generated by breaking waves. When steep waves break repeatedly over sandbars, they push significant volumes of water toward shore. That water seeks escape routes back to deeper areas. The resulting rip currents can form rapidly during building surf. Because waves on the Great Lakes can increase quickly during storms, rip currents may develop in a matter of hours. A beach that was calm in the morning may host strong outward currents by afternoon. Visual cues are subtle. Slight discoloration in the water or a gap in breaking waves may indicate the presence of a rip channel. Understanding wave behaviour requires abandoning the assumption that freshwater equates to gentler motion. In many ways, the lake's waves are more abrupt than ocean swells. Their tight spacing and steep faces demand constant attention. Standing on shore, watching waves crash against rocks can be mesmerising. The repetition feels almost mechanical. Yet within that repetition lies variation. Every set differs slightly. Interference shifts peak heights. Wind gusts alter timing. It is easy to see why early sailors on these lakes sometimes compared them to inland seas. The scale alone supports the comparison. But the wave dynamics, shaped by enclosure and depth variation, add their own distinct character. Respecting that character means adjusting expectations. A forecast predicting 6-foot waves on Lake Michigan may not sound severe to someone imagining slow ocean rollers. In reality, 6-foot short period waves can create conditions that feel far more aggressive than their height suggests. Boaters who plan routes based solely on wave height, without considering period and direction, risk underestimating difficulty. The Great Lakes reward those who read beyond surface numbers. Wave forecasts now include period and direction data. Marine advisories highlight potential cross-sea conditions. Yet interpretation requires familiarity with how these variables translate into lived experience. The water does not follow simplified mental models. It follows physics shaped by glacial basins, wind corridors, and shoreline geometry. And when those waves finally break against cold freshwater surfaces under strengthening winds, they reveal another layer of hazard that is less visible, but equally unforgiving. The temperature of the water itself, and how quickly it can overwhelm the human body once immersion occurs. There is a particular kind of confidence that warm air creates. On a bright summer afternoon along Lake Michigan or Lake Huron, the sun reflects off the surface. Sand heats underfoot. Children run toward the water without hesitation. The air might be 85 degrees, the sky clear. The lake appears inviting, almost gentle. What the air does not reveal is the temperature waiting just below the surface. The Great Lakes are cold for most of the year, not cool, not brisk. Cold in a way that carries physical consequences within minutes. Because of their immense depth and volume, these lakes store winter in their lower layers long after spring arrives. Surface water may warm in shallow coastal areas, but only a short distance offshore, temperatures drop sharply. Even in midsummer, deeper sections of Lake Superior often remain in the 40s Fahrenheit. That temperature difference is not obvious from above. A swimmer wading into shallow water may feel only mild coolness. After a few strokes outward, especially if a drop-off occurs, the body can suddenly enter significantly colder water. That shift can trigger what is known as cold shock. Cold shock is not gradual discomfort. It is immediate. When the body is immersed in water below roughly 60 degrees Fahrenheit, the skin's temperature receptors signal an abrupt stress response. Breathing rate spikes, an involuntary gasp reflex may occur. Heart rate increases sharply, lasts only a few minutes, but it is one of the initial phases of drowning, lasts only a few minutes, but it is one of the most dangerous. Panic often compounds the reaction. Muscles tense, breathing becomes rapid and shallow. Clear thinking becomes more difficult. In choppy conditions, simply keeping the airway clear can be challenging, and the Great Lakes, even on relatively calm days, rarely remain perfectly still. After the initial cold shock phase, the next concern is cold incapacitation. As the body loses heat to the surrounding water, muscle function begins to decline. Water conducts heat away from the body approximately 25 times faster than air at the same temperature. In fresh water that hovers around 50 degrees, loss of dexterity can occur in as little as 10 to 15 minutes. Fingers lose grip strength. Arms tire quickly. Swimming becomes less efficient. People often overestimate their ability to swim in cold water. In controlled environments like heated pools, endurance feels manageable. In open freshwater with waves and wind, physical decline accelerates. Hypothermia follows. Hypothermia occurs when core body temperature drops below 95 degrees Fahrenheit. In cold Great Lakes water, this can develop faster than many realize. Survival time depends on multiple factors, including water temperature, body composition, clothing, and movement. At 50 degrees Fahrenheit, exhaustion or unconsciousness can occur in under an hour without protective gear. In 40-degree water, that window shortens further. Lake Superior in early spring may still hold large areas in the 30s and low 40s. The cold does not negotiate with fitness level or swimming experience. Even strong swimmers experience rapid heat loss. The body's response to cold immersion is physiological, not psychological. Determination alone does not slow the process. One common misconception involves air temperature. On a day when the air reaches 75 or 80 degrees, the water may still be 50. People stepping off boats or diving from docks often gauge risk based on how warm they feel above the surface. The disconnect between air and water temperature is a frequent factor in accidents. Wind adds another dimension. Wind chill does not affect water temperature directly, but it influences how quickly someone cools once partially submerged. After exiting cold water, evaporation from wet clothing in strong wind accelerates heat loss. Boaters without proper gear who become soaked in rough conditions may begin cooling rapidly even before re-entering water. Freshwater density also affects buoyancy slightly. Salt water provides more buoyant support due to its higher density. In freshwater, the body sits marginally lower. This difference is subtle but matters when energy reserves decline. Keeping the airway above water requires slightly more effort. Life jackets dramatically extend survival time in cold water. By maintaining buoyancy, a life jacket reduces the need for active swimming. It allows individuals to conserve energy and adopt positions that minimize heat loss, such as the heat escape lessening posture, where knees are drawn toward the chest. Despite this, many recreational boaters on the Great Lakes forego life jackets during calm weather. The illusion of safety created by still water extends to temperature assumptions. Because the surface looks manageable, the underlying cold is not considered. Ice cover during winter reinforces the lake's low temperatures. In colder months, sections freeze over. Even when ice begins to break apart in spring, underlying water remains near freezing. Early season anglers or paddlers sometimes underestimate just how cold the water remains beneath patchy ice remnants. rescue operations in such conditions face extreme urgency. In near-freezing water, time to unconsciousness can be measured in minutes. Rescue teams train for cold water retrieval, but distance and weather conditions complicate response. There are also cases of sudden immersion during storms. A boater knocked overboard by a steep wave during autumn may enter water in the 40s. Even with a life jacket, muscle control declines quickly. Climbing back aboard becomes difficult. In addition to temperature, the psychological impact of cold immersion is significant. The body's stress response narrows focus. Decision-making becomes reactive. Fine motor skills deteriorate. Tasks like unzipping compartments, grasping ropes, or activating communication devices become harder. Cold water incidents often unfold faster than anticipated. Another factor unique to large freshwater systems is upwelling. Upwelling occurs when strong winds push surface water away from a shoreline, allowing colder, deeper water to rise and replace it. This can cause sudden drops in nearshore water temperature, sometimes by 10 to 20 degrees in a matter of hours. A beach that felt comfortably cool one day may feel sharply cold the next due to upwelling. Swimmers unaware of this shift may enter water expecting familiar conditions and encounter temperatures low enough to trigger cold shock. Divers experience similar challenges. Descending through thermoclines, layers where temperature changes abruptly with depth, can result in rapid cooling. Without proper suits, extended exposure becomes dangerous. The cold also preserves. Shipwrecks resting at depth remain intact longer in freshwater, partly because of the low temperatures and absence of certain saltwater organisms. While this preservation fascinates divers and historians, it underscores how consistently cold these waters remain. The Great Lakes' depth ensures that seasonal warming does not fully penetrate the water column. Lake Erie, being shallower, warms more thoroughly in summer, yet even there storms can mix colder bottom water upward temporarily, reducing surface temperatures quickly. Lake Superior's average temperature remains lower year-round due to its immense depth and northern latitude. The cold that shapes these lakes is not dramatic on the surface. It is quiet and constant. Unlike waves, which can be seen building, temperature differences hide below a thin reflective layer. People sometimes describe cold fresh water as refreshing, and in controlled settings, brief exposure can be invigorating. The difference lies in duration and preparedness. Short, intentional immersion differs significantly from accidental entry during storms. Understanding cold risk changes behaviour. Wearing thermal protection during early season boating becomes a precaution rather than an overreaction. Checking water temperature before swimming becomes routine. Keeping flotation devices accessible becomes standard practice. The lakes do not warm quickly in response to a few hot days. They respond to seasonal cycles shaped by glacial depth and atmospheric patterns. Even in late summer, deeper water remains cold enough to impair swimmers unexpectedly. This cold is not aggressive, it is not dramatic, it simply extracts heat according to physical law. It does not respond to intention, skill or urgency, and when combined with waves driven by sudden storms or currents formed along irregular shorelines, the temperature becomes part of a broader system that demands respect. Because while wind and waves may draw attention first, it is often the water's quiet, steady cold that determines survival time once someone is immersed, especially when currents beneath the surface begin moving in directions that are not immediately visible from above. From the shoreline, water often looks like it moves in simple patterns. Waves roll in, foam spreads thinly across the sand, the surface rises and falls in repeating motion. It feels directional, almost straightforward. Water comes toward land, then retreats. But beneath that visible motion, the Great Lakes are constantly shifting in ways that are far less obvious. Currents form not only from tides, which the lakes largely lack, but from wind, shoreline shape, underwater contours, river inflow, and even differences in water temperature. These forces combine into pathways of movement that are invisible from eye level. And it is often these unseen flows, rather than dramatic waves, that create the most immediate danger for swimmers and small craft. One of the most common and misunderstood currents on the Great Lakes is the rip current. Many people associate rip currents exclusively with ocean beaches. In reality, they are just as common on large freshwater lakes, especially along Lake Michigan and Lake Huron. The physics are the same. When waves break along a shoreline, they push water toward land. That water accumulates between the breaking point and the beach. It must return to the lake somehow. Often, it escapes through narrow channels in sandbars or gaps between underwater ridges. The returning water funnels outward in a concentrated stream. From above, a rip current may appear as a darker patch of water or a break in the pattern of incoming waves. From standing height at the beach, however, it often looks no different from the surrounding surface. Swimmers caught in a rip current frequently describe the sensation as being pulled directly away from shore. The current itself does not pull downward. It moves horizontally, carrying water back into deeper sections of the lake. The danger arises from instinct. The natural reaction is to swim directly against the current toward land. But rip currents can move faster than an average swimmer can sustain. Fighting directly against them leads to exhaustion. Panic follows. Breathing becomes irregular. The correct response is to swim parallel to shore, moving out of the narrow channel where the current is strongest. Once free of the outward flow, returning to shore becomes much easier. This strategy requires awareness and composure, both of which can be difficult in cold water with waves breaking around you. Rip currents intensify during periods of strong onshore wind. As storm-driven waves build, more water is pushed toward land. The return flow strengthens accordingly. Beaches that were calm in the morning can host powerful rip currents by afternoon as wind increases across the basin. Structural currents add another layer. Piers, jetties, and breakwalls are common along Great Lakes shorelines. These structures alter how waves interact with the beach. When waves approach at an angle, water can accumulate along one side of a pier before being forced outward along its edge. This creates a channel of fast-moving water adjacent to the structure. Swimmers drawn toward piers, either intentionally or by drifting, may suddenly encounter strong outward flow. Combined with waves reflecting off the structure, the water becomes turbulent. The presence of these currents is rarely obvious without experience. Longshore currents operate differently but can still pose risk. When waves strike the shoreline at an angle, they push water sideways along the beach. This sideways movement can gradually carry swimmers far from their original entry point without them realizing it. Someone may begin swimming directly out and back relative to their position on shore. Over time, they may drift dozens of yards down the beach. Returning to the exact entry point becomes disorienting. For small craft, longshore currents can complicate navigation near shore, especially in combination with wind-driven surface movement. Wind itself drives large-scale surface currents across the lakes. When sustained winds blow in one direction for hours or days, they push the upper layer of water along with them. This movement can create significant differences in water level between opposite ends of a basin. As mentioned earlier, this setup can trigger seeches, oscillations where water sloshes back after wind relaxes. During these oscillations, currents can shift direction unexpectedly. A harbour that experienced outward flow earlier in the day may experience inward surge hours later, even without active wind. Temperature differences contribute to vertical currents. When surface water warms and deeper water remains cold, stratification forms. Strong winds or storms can disrupt this layering, mixing water columns. As deeper water rises and surface water sinks, localized vertical currents develop. While these vertical movements are usually less noticeable to swimmers, they influence temperature distribution and underwater navigation conditions for divers. River inflow also shapes current patterns. Major rivers feed into the Great Lakes, bringing fresh water, sediment, and varying temperatures. At river mouths, water flow into the lake can create localized current zones. After heavy rainfall, increased discharge strengthens these flows. Boaters and swimmers near river outlets may encounter unexpected movement where inflowing water meets lake currents. The scale of the lakes allows these currents to exist simultaneously in different areas. On a given day, rip currents may be active along one stretch of shoreline, longshore currents dominating another, and surface wind-driven flow moving across open water miles offshore. Because there are no significant tidal cycles to create predictable twice-daily current reversals, patterns depend more heavily on recent wind history. That history matters. Currents can persist after visible waves have diminished. A storm that built strong rip currents in the afternoon may leave residual outward flow into the evening. Swimmers entering the water once the surface appears calmer may assume conditions have returned to normal. Underwater topography amplifies these flows. Glacial carving left ridges and drop-offs across the lake floor. Water moving over uneven terrain accelerates through narrow channels and slows in broader sections. These variations are not visible from the surface. In some cases, sandbars create shallow zones followed by abrupt deeper troughs. Waves breaking over the bar push water into the trough. That water then escapes through specific low points in the bar, forming rip currents. Because sandbars shift over time due to storms and seasonal sediment movement, current locations change as well. The absence of salt does not reduce current strength. Fresh water behaves according to the same fluid dynamics as salt water. Density differences are minor compared to the forces generated by wind and wave energy. For boaters, currents influence maneuverability. A small motorboat attempting to dock in a marina during strong longshore current may find steering less responsive. The current pushes the hull sideways. Combined with crosswinds, control becomes more complex. Kayakers crossing between points along a shoreline may underestimate how much lateral drift occurs during sustained wind-driven flow. For divers exploring shipwrecks, currents at depth can differ from surface conditions. While surface water may appear relatively calm, deeper layers may still be moving due to previous wind forcing. Anchoring lines can angle unexpectedly. Ascending without accounting for drift can lead to surfacing far from entry points. Rescue operations must consider current patterns carefully. When someone goes missing offshore, search areas expand based on wind speed, direction, and known current flows. Estimating drift requires analysing both surface and subsurface movement. Cold water compounds current danger. A swimmer caught in a rip current in warm tropical water faces exhaustion risk primarily from panic and fatigue. On the Great Lakes, the same situation often unfolds in colder water. As muscle strength declines due to temperature, the margin for error shrinks. Life jackets significantly reduce risk in current situations. By preserving buoyancy, they allow individuals to float and signal for help rather than attempting continuous swimming against flow. Public awareness campaigns along Great Lakes beaches increasingly emphasize rip current education. Flag systems and signage aim to reduce surprise encounters, yet the currents remain largely invisible until experienced directly. From shore, the lake may look flat and uniform. The surface reflects sunlight evenly. There is no visible arrow pointing outward. Understanding currents requires shifting perspective. Instead of seeing waves as simple in and out motion, it helps to imagine the entire shoreline as a dynamic system where water is constantly seeking balance. Every wave that pushes toward land adds volume to the near-shore zone. That volume must return outward. The path it takes depends on bottom shape, structures, and wind. The lake's size ensures that wind energy accumulates across wide expanses. That energy converts into wave action, and wave action generates current. It is procedural, continuous, and indifferent. Recognizing the presence of these hidden movements changes how one approaches the water. Entering between piers during strong surf becomes an informed decision rather than a casual one. Swimming parallel when caught in outward flow becomes instinctive rather than counterintuitive. Because beneath the surface of what looks like a single, unified body of water lies a network of moving channels shaped by wind, depth, and shoreline design. And when those movements combine with limited visibility or shifting weather, orientation itself can begin to falter in ways that feel far less predictable than the water's surface might suggest. We tend to believe that risk increases as we move farther out beyond the buoys, beyond where your feet no longer touch the bottom, beyond the last anchored boat. We tend to believe that risk increases with distance from land, and that proximity to the shoreline offers a kind of built-in protection. On the Great Lakes, that assumption has led many people into situations they did not anticipate, because the shoreline feels familiar. There are dunes and picnic tables, parking lots and paved paths, families with coolers and umbrellas. The environment looks organised, structured, human. It does not resemble a remote coastline battered by salt and storm, but the physics do not change simply because there is sand beneath your feet. Many of the most dangerous incidents on the Great Lakes occur not miles offshore, but within sight of the beach. Rip currents form near shore. They do not require deep open water to function. In fact, they are strongest in the breaking zone where waves collapse over sandbars and push water toward land. The return flow begins only yards from dry sand. A swimmer standing waist deep may not notice that the water moving around them has direction. A few steps farther, and they can find themselves in a narrow outward moving channel. The shoreline does not signal where these channels are. Unlike ocean beaches that often have lifeguard towers scanning for subtle colour changes in the water, many Great Lakes beaches are unguarded. The absence of flags or whistles can create a false sense of security. Even on guarded beaches, conditions can shift throughout the day as wind increases or changes direction. Another misconception involves breakwalls and piers. These structures feel solid and protective. They extend into the water like arms. People walk along them to fish or watch waves. They appear to divide the lake into manageable sections. In reality, they reshape water movement in ways that intensify local currents. When waves strike a breakwall, they reflect outward. Incoming waves collide with those reflections. Water forced toward the structure must escape somewhere, often along its sides. Swimmers entering the water near piers during active surf frequently encounter strong outward currents along the edges. The structure that looks like shelter becomes a boundary that channels energy. Storm watchers sometimes stand on breakwalls during high wave events. It feels stable underfoot. The view is dramatic. But waves do not always break predictably. Larger sets can overtop walls unexpectedly, knocking people off balance and into turbulent water below. The myth of the safe shoreline also extends to water depth. Many beaches slope gradually at first. Waders may walk out several yards before water reaches chest level. This gradual slope creates confidence, but sandbars often create uneven bottom contours. A shallow stretch may be followed abruptly by a deeper trough. When waves break over the sandbar, they may appear manageable. Just beyond it, in the trough, the water can deepen quickly. If someone is standing on the bar and steps unexpectedly into the deeper section, balance shifts. Combined with incoming waves, footing can disappear. Cold water amplifies this risk. In early summer, when air temperatures are warm but water remains cold, people enter the lake expecting comfort. A sudden step into deeper, colder water can trigger cold shock. The gasp reflex does not require deep offshore conditions to activate. Shoreline crowds can create social pressure. When others are swimming or wading, the environment feels collectively safe. Individuals are less likely to question conditions if dozens of people are already in the water. But water does not adjust its behaviour based on crowd size. Large groups may enter during moderate surf, unaware that rip currents are active in certain sections of the beach. If multiple people become distressed simultaneously, rescue becomes more complicated. Wind-driven waves also behave differently near shore than people expect. As waves move into shallower water, they steepen. A wave that appeared moderate from a distance can break with more force as it approaches land. Body surfers and children playing in the break zone may underestimate the force of a steep, collapsing wave. Even a wave only a few feet high can knock someone off their feet and drive them into the bottom. The lake floor is not always soft sand. In many areas, rocks, submerged logs and uneven terrain lie beneath the surface. Being thrown by a breaking wave into shallow water can result in injury. The absence of tides further complicates perception. Ocean beaches often display clear tidal lines. Wet sand marks recent high tide. Exposed rocks indicate low tide. On the Great Lakes, water levels fluctuate more subtly through seeches and seasonal changes. A beach that appears wide and dry in the morning may experience rising water later in the day due to sustained wind pushing water toward that shoreline. Visitors may not recognize that the lake level has shifted slightly. The shoreline can narrow unexpectedly during strong onshore wind events. In some cases, waves and elevated water levels reduce available dry sand significantly. Escape routes from incoming waves shrink. People standing near the waterline may find themselves closer to breaking surf than anticipated. River mouths add another hidden layer. Beaches located near river outlets often experience mixed current patterns. River water entering the lake creates outward flow. When combined with wave-driven return currents, complex movement patterns form near shore. Swimmers drawn toward calmer-looking water near a river mouth may unknowingly enter zones of stronger current. Temperature differences near shore can also deceive. On certain days, surface water warmed by sun may sit above colder layers. Children playing in knee-deep water feel warmth and assume conditions are consistent. A few yards beyond, if a deeper pocket exists, water temperature can drop sharply. Sudden immersion into colder water disrupts breathing and balance. Shoreline cliffs and bluffs present another risk. In some areas along Lake Superior and Lake Michigan, high bluffs rise above the water. Jumping from these heights into the lake may seem appealing on hot days, but water depth below cliffs can vary seasonally. Sand movement and erosion alter bottom contours. A location that was deep enough one year may not be the next. Even where depth is sufficient, cold water shock and waves can disorient jumpers upon entry. The myth of safety extends into winter as well. When lakes freeze near shore, ice appears solid. People walk out to fish or explore. The presence of footprints or vehicles may create confidence. Ice thickness, however, is not uniform. Currents beneath the surface thin certain sections. River mouths and areas with subsurface movement remain weaker. A shoreline that appears stable may conceal thinner ice only yards farther out. In spring, melting ice near shore can create unstable conditions as well. Ice shelves along beaches sometimes look solid but may be undercut by waves beneath them. Standing on such shelves during active surf can be hazardous. Public infrastructure reinforces the sense of security. Boardwalks, restrooms, lifeguard chairs, and designated swimming areas suggest oversight and control. While these features improve safety when used properly, they can also signal that risk is minimal. In reality, designated swimming areas often exist precisely because certain sections of shoreline are known to be hazardous. The Great Lakes do not present uniform conditions along every beach. A calm cove may exist a mile away from a section experiencing strong rip currents. Wind direction relative to shoreline orientation determines which areas are more exposed. Understanding this requires awareness of larger basin dynamics, not just what is visible from the parking lot. The shoreline is a transition zone. It is where wave energy releases. It is where water returning from land meets incoming swell. It is where bottom contours shift most dramatically. It is not the safe edge of danger. It is often where energy concentrates. Recognizing this shifts behavior. Entering water away from piers during high surf becomes deliberate rather than accidental. Checking posted conditions becomes routine. Understanding that most drownings occur within sight of shore reframes distance assumptions. The lake does not distinguish between those a mile offshore and those 30 feet from sand. Its currents, waves, and temperature gradients operate continuously, and when visibility drops due to fog or sudden weather changes, that familiar shoreline can lose its visual anchors quickly, turning what felt like a stable boundary into something far less certain. There are days on the Great Lakes when the horizon simply disappears, not dramatically, not with thunder or sudden wind. It fades. One moment, you can see a clean line where water meets sky. The next, that line softens into grey. Shorelines blur. Boats in the distance become shadows. Within minutes, the world feels smaller. Fog over the Great Lakes is not unusual. It is a natural product of temperature differences between air and water. When warm, moist air moves over colder lake surfaces, the air cools rapidly. As it cools, moisture condenses into tiny droplets suspended in the air. Those droplets scatter light. Visibility drops, sometimes to less than a few hundred feet. From shore, fog can look peaceful. It softens sound. It creates stillness. But for anyone on the water, it removes the single most important orientation tool humans rely on: sight. Distance becomes distorted first. On a clear day, scale is already difficult to judge across open water. The opposite shore of Lake Michigan may not be visible at all from certain points. Without landmarks, estimating miles becomes guesswork. Add fog, and even nearby reference points disappear. A boat leaving harbour may intend to travel only a short distance offshore. As visibility declines, turning back becomes less straightforward. The harbour entrance may no longer be visible. Navigational markers vanish into grey. Without GPS or compass use, direction becomes uncertain quickly. Humans are not naturally good at maintaining straight-line travel without visual reference. Studies in psychology and survival training show that when deprived of landmarks, people tend to move in gradual arcs rather than straight paths. On open water, this tendency can lead to significant drift. Wind and current continue moving the boat while orientation fades. Fog also alters sound perception. Over water, sound travels efficiently. In fog, it can seem amplified or displaced. An engine heard faintly may seem closer than it is. A foghorn may echo unpredictably. Determining direction based solely on sound becomes unreliable. Commercial vessels operating in heavy fog rely on radar and established navigation protocols. Recreational boaters may not have access to the same equipment or training. Even kayakers and paddleboarders close to shore can become disoriented. A short paddle parallel to the beach may feel manageable in light fog, but if wind shifts and pushes the craft slightly outward, the shoreline can disappear completely. Without clear visual contrast between water and sky, the brain struggles to distinguish up from forward. There is also a subtle psychological effect. When visual cues are limited, the mind fills gaps with assumption. A faint shape in the distance may be interpreted as land when it is actually cloud. The absence of a visible shoreline can create mild panic, even when physically close to safety. Disorientation increases heart rate. Decision-making narrows. Small navigation errors compound. Fog interacts with wave behaviour as well. Without seeing wave sets approaching from a distance, boaters cannot anticipate larger crests. They respond only when the wave is already beneath them. Reaction time decreases. On calmer days, fog may coincide with relatively flat water. The absence of wind can produce thick, low-lying fog banks. This stillness enhances the illusion of safety. Because the surface is smooth, people may underestimate how far they have drifted. Without noticing subtle current or wind movement, a boat can move steadily offshore, while its occupants believe they remain near their original location. The Great Lakes' size amplifies this effect. On smaller lakes, even in fog, shoreline may remain faintly visible in at least one direction. On Lake Superior or Lake Michigan, open stretches of water can extend beyond visibility even on clear days. In fog, that openness becomes total. Boaters navigating across these expanses rely entirely on instruments. Compass headings must be maintained consistently. GPS coordinates must be checked frequently. Drift must be accounted for. For those without these tools, returning to a specific harbour entrance becomes a challenge. Fog is not limited to summer mornings. In autumn, when warm fronts pass over cold lake surfaces, advection fog can form rapidly. During winter, steam fog can rise when extremely cold air moves across comparatively warmer water. These seasonal variations mean fog risk exists across much of the year. Distance perception is altered not only by fog but also by the sheer scale of the lakes. On clear days, the curvature of the Earth hides distant objects below the horizon. A large freighter may appear gradually from the top down as it approaches. Without experience, judging how far away it is can be difficult. A boat that appears small and distant may actually be several miles closer than assumed. Conversely, a faint shape on the horizon may be far larger and farther away than it seems. These misjudgments matter during crossings. For example, a recreational boater planning to cross Lake Huron from one side to the other may look at a map and see a straight line. On the water, that line translates into hours of travel without visible land on either side. If fog develops mid-crossing, orientation depends entirely on navigation tools. Fatigue plays a role here as well. Maintaining precise headings over long distances requires focus. Minor steering adjustments accumulate over time. A slight deviation sustained for an hour can place a boat miles off intended course. Wind rarely blows in a perfectly consistent direction. Even subtle shifts push vessels sideways, a phenomenon known as leeway. Without constant correction, boats drift. For paddlers, this effect is pronounced. A kayak crossing even a few miles of open water can be pushed significantly off course by moderate crosswinds. In fog, the paddler may not realise the drift until attempting to locate a landing point. The shoreline, once visible, may now lie at an unexpected angle. Large commercial ships mitigate disorientation with established shipping lanes, radar systems and strict procedures. Smaller craft rely more heavily on individual judgment. Fog also increases collision risk. Reduced visibility limits reaction time between vessels. Sound signals are required in heavy fog, but not all recreational boats carry appropriate equipment or understand proper signalling patterns. The Great Lakes' heavy shipping traffic, especially in certain corridors, means large freighters may be moving even when visibility is low. A small craft without radar may not detect an approaching vessel until it is very close. From shore, fog may feel atmospheric and calm. Photographers often capture images of lighthouses emerging from mist. The mood appears tranquil. But for those within it, especially without preparation, the experience can shift from peaceful to unsettling quickly. Disorientation is not always dramatic. It can begin as a subtle uncertainty about direction, a feeling that the shoreline should be visible but is not, a glance at the compass revealing unexpected headings. That small uncertainty grows if not addressed. Training and preparation reduce risk significantly. Carrying a compass and knowing how to use it. Understanding that wind direction influences drift. Checking weather forecasts not only for wind speed but also for temperature differences that may generate fog. Even simple habits, such as noting a compass bearing when leaving harbour, make returning easier if visibility drops. The lakes themselves are not altered by fog. Waves, currents, and temperature gradients continue unaffected. It is human perception that changes. When vision narrows, reliance on other senses increases. When those senses provide incomplete information, stress rises. The combination of large-scale water, shifting wind, cold temperature, and limited visibility creates scenarios where minor miscalculations become significant. Standing on a beach as fog rolls in, you may notice how quickly the world feels contained. The lake seems smaller, closer. In reality, it remains vast. And when storms begin to form beyond that hidden horizon, intensifying out of sight, the lack of visibility can conceal the earliest signs of changing weather until the effects arrive with far less warning than expected. For centuries, people have crossed the Great Lakes with confidence. Cargo ships loaded with iron ore and coal, wooden schooners carrying grain, steamers transporting passengers between growing industrial cities. The lakes became economic highways, linking inland ports to global trade routes through the St. Lawrence Seaway. From a map, the system appears efficient. 5 connected basins, clearly defined channels, lighthouses marking entrances and shoals. It looks organised, and yet thousands of ships lie at the bottom. More than 6,000 documented wrecks rest beneath the Great Lakes, and historians believe the true number may be much higher. Some vessels sank in storms, others collided in fog, a few ran aground due to navigation errors, many simply disappeared during severe weather events, their final moments known only through fragmented radio transmissions or scattered debris. The lakes preserve these wrecks in a way oceans do not. Cold fresh water slows corrosion. The absence of salt reduces deterioration. Wooden hulls remain intact far longer than they would in salt water. Divers exploring wreck sites sometimes describe ships as frozen in time, cargo holds still visible, masts still standing. That preservation makes the losses feel closer. One of the most well-known incidents occurred in November 1975, when the SS Edmund Fitzgerald sank on Lake Superior during a powerful storm. The vessel was 729 feet long, carrying iron ore from Minnesota to Michigan. All 29 crew members were lost. The storm that night produced winds exceeding 50 miles per hour and waves reportedly reaching over 20 feet. Communication with the ship ceased abruptly. Despite extensive search efforts, no survivors were found. The scale of that ship matters. It was not a small wooden schooner vulnerable to every gust. It was a massive steel freighter built specifically for Great Lakes conditions. Its disappearance underscored a difficult truth. Size alone does not guarantee safety against short-period steep freshwater waves driven by powerful wind systems. The Fitzgerald was not unique. Throughout the 19th and early 20th centuries, wooden ships were frequently lost during autumn gales. Before modern forecasting, captains relied on barometers and experience. When pressure dropped rapidly and wind increased, options were limited. Harbours were not always nearby. Sailing vessels could not outrun storms. Steam-powered ships later improved manoeuvrability, but remained vulnerable to wave stress and navigation challenges in fog. The lakes earned a reputation among mariners for sudden escalation. Storm systems in November became particularly feared. Cold air sweeping across relatively warm lake surfaces intensified low-pressure systems. Waves built quickly across long fetches. Snow and freezing spray reduced visibility and added weight to decks. Freezing spray presented its own danger. When waves crashed against hulls in sub-freezing air, water droplets froze upon contact. Ice accumulated on railings, superstructures and rigging. This added weight high above the waterline, affecting stability. Ships listing slightly due to cargo shift could become more unstable as ice built up unevenly. Some vessels foundered not only because of wave impact, but because accumulating ice compromised balance. Fog played a role in many wrecks as well. In heavy fog, visibility dropped to near zero. Before radar became standard equipment, ships navigated by compass, dead reckoning, and sound signals. Two vessels approaching one another in limited visibility faced collision risk, if timing or positioning was misjudged. The Great Lakes' confined channels and busy shipping lanes increased the stakes. The loss of the SS Eastland in 1915 in the Chicago River, though not on open lake water, highlighted how even docked vessels could be affected by stability issues. The ship rolled while tied to the dock due to design flaws and uneven weight distribution, resulting in significant loss of life. While that incident differed from open water storm losses, it underscored how freshwater maritime environments required precise engineering and careful loading. The lake's bottom topography contributed to shipwrecks too. Reefs and shoals carved by glacial action created underwater hazards. Before detailed hydrographic mapping, captains relied on charts that were not always complete. In low visibility or heavy weather, grounding became a real risk. Lake Superior's rocky northern shoreline in particular claimed many vessels that were driven onto submerged outcrops during storms. Human factors cannot be ignored. Fatigue during long voyages, pressure to meet delivery schedules, and incomplete weather information influenced decision-making. Captains sometimes chose to press forward rather than seek shelter, weighing economic urgency against risk. Once offshore, turning back could be more difficult than continuing forward, especially as conditions deteriorated. Even in modern times, with advanced radar, satellite forecasting, and reinforced hull designs, the lakes continue to demand caution. Large freighters operating today monitor weather closely. Marine forecasts provide wave height, period, and wind direction. Yet captains still adjust routes to avoid the worst of autumn storms. Smaller recreational vessels remain particularly vulnerable. Unlike commercial ships designed specifically for Great Lakes service, pleasure craft vary widely in size and construction. A boat that handles moderate chop well may struggle in steep, short-period storm waves. When caught offshore during rapidly building weather, options narrow quickly. Search and rescue operations on the Great Lakes are extensive and well coordinated. The United States Coast Guard and Canadian authorities maintain stations across the region. Helicopters, cutters, and smaller rescue boats respond to distress calls, but response times depend on conditions. High waves, strong winds, and limited visibility complicate operations. Even with modern technology, reaching a vessel in distress can take time. The lake's size matters here. Lake Superior alone spans more than 31,000 square miles. Searching for a small craft in heavy seas across that expanse presents logistical challenges. Cold water further reduces survival windows. If a vessel capsizes during autumn or spring, crew members entering water in the 40s or low 50s Fahrenheit face rapid cold shock and hypothermia. Even with life jackets, survival time may be measured in hours. The preservation of shipwrecks beneath the lakes offers historical insight but also serves as quiet testimony. Divers exploring sites often report remarkable clarity. Cold, fresh water slows biological growth. In some cases, ship names remain legible on hulls. These wrecks are not distant relics from ancient history. Many occurred within the past century. Lighthouses line the Great Lakes for a reason. Built to guide ships through narrow passages and around shoals, they represent efforts to reduce loss. Each light marks an area where navigation once proved difficult. The number of lighthouses across the region reflects how frequently vessels encountered hazards near shore. Even with these aids, storms have overwhelmed navigation systems. There are accounts of ships losing radio contact mid-transmission, as waves pounded decks and wind roared across steel structures. Distress signals cut short, debris found days later. The lake's enclosed nature means wreckage often remains within the basin, rather than drifting out to open ocean. Communities along the shores carry stories of these losses. Maritime museums display artifacts recovered from depths. Families remember crew members who never returned home. The phrase, "never came home," is literal. Ships left port under ordinary conditions, cargo secured, routes planned, weather assessed. And somewhere between departure and destination, forces beyond control intervened. Understanding these histories reshapes perception. The Great Lakes are not recreational ponds that occasionally misbehave. They are dynamic freshwater seas that have tested engineering, navigation, and human judgment repeatedly. Technology has reduced risk significantly over time. Hull designs improved, forecasting became more accurate, communication systems advanced. Yet the fundamental forces remain. Wind across long fetch, short steep waves, cold water, rapidly developing storms. Standing on a beach today, watching a freighter move steadily across the horizon, it is easy to assume control. The ship appears small against the expanse, yet solid and deliberate. Beneath that surface lies history, shaped by vessels that did not complete their journeys. And while storms claim attention, many losses were preceded not by dramatic sky-darkening moments, but by seasonal shifts that quietly intensified the lake's behaviour in late autumn, when cold air and retained warmth combine into what locals have long called the Witch of November. By the time November arrives around the Great Lakes, something subtle has already shifted. The beaches are quieter, marinas thin out, trees along the shoreline shed their leaves. The air sharpens in the mornings. It feels like a closing chapter of the year, a slowing down. But beneath that seasonal calm, the lakes are holding on to something. All summer long they absorbed heat. Sunlight penetrated the upper layers. Surface temperatures rose. Even as air temperatures begin to fall in autumn, the deeper water remains comparatively warm. It releases that stored energy slowly. This contrast between cooling air and retained water warmth sets the stage. Locals have long referred to the powerful late-season storms that sweep across the region as the Witch of November. The name carries a sense of personality, but the mechanics are straightforward. Cold, dry Arctic air masses begin moving southward more frequently in late autumn. At the same time, warmer, moist air from lower latitudes can still push north. When these systems meet over the Great Lakes, the temperature gradient becomes pronounced. Warm water below, cold air above. As cold air passes over the relatively warmer lake surface, heat transfers upward. That heat destabilizes the lower atmosphere. Pressure drops. Air begins to rise. Surrounding air rushes in to fill the space. Wind strengthens. Low-pressure systems tracking across the upper Midwest often deepen as they interact with the lakes. The basin effectively fuels the storm. What may have begun as a moderate system over land can intensify over water. Winds during these November storms frequently exceed 50 miles per hour. Gusts may climb higher. Sustained winds across long fetch produce waves that grow rapidly in height and steepness. Lake Superior, with its vast open expanse, is particularly susceptible. A strong northwest wind can travel hundreds of miles uninterrupted across the lake's surface. By the time that energy reaches the southeastern shore, waves can exceed 20 feet. In extreme cases, waves have been recorded even higher. Unlike ocean swells that roll in long, predictable intervals, Great Lakes waves during November gales are tightly spaced. Short periods mean vessels have little recovery time between crests. The combination of height and steepness creates punishing conditions. Autumn storms also bring rapidly changing precipitation. Rain may shift to sleet, sleet to snow. Temperatures can hover near freezing, creating additional hazards. Spray kicked up by breaking waves can freeze upon contact with exposed surfaces. Freezing spray is particularly dangerous for ships. When water freezes on decks and superstructures, it adds weight unevenly. Ice accumulation raises a vessel's centre of gravity. Stability decreases. Even large freighters must monitor ice build-up carefully during these conditions. Smaller craft face even greater vulnerability. By November, many recreational boaters have already pulled their vessels for the season. But commercial traffic continues. Cargo still moves. Late-season fishing operations still occur. The Witch of November does not respect schedules. One of the defining characteristics of these storms is duration. Unlike brief summer squalls that pass within an hour, November systems can persist for days. Sustained wind over long periods allows wave energy to build fully. The lake does not have time to settle between gusts. Water levels may shift dramatically as wind pushes surface water toward one end of a basin. Seiches develop. Shorelines experience temporary surges. Harbours that were sheltered become exposed as wind direction rotates. Visibility often deteriorates. Blowing snow reduces contrast between sky and water. The horizon disappears. During nightfall, navigating in heavy seas under such conditions becomes intensely challenging. It was during one such November storm in 1975 that the Edmund Fitzgerald was lost on Lake Superior. That particular storm combined strong sustained winds with significant wave height. Communication between ships indicated severe conditions. Then, abruptly, contact was lost. The scale of that loss etched November storms into regional memory. But the Fitzgerald was not the only vessel claimed during late autumn gales. Throughout the 19th and early 20th centuries, November wrecks were common. Wooden schooners, steamers, and later steel freighters encountered conditions that exceeded their design tolerances. Before modern forecasting tools, captains relied heavily on barometric pressure readings and sky observation. A rapidly falling barometer signalled trouble. But once offshore, options were limited. Seeking shelter required reaching harbour before the storm intensified. In many cases, distance made that impossible. Even today, with satellite imagery and advanced modelling, November storms demand caution. Marine forecasts for the Great Lakes include gale warnings and storm warnings. Wave height predictions account for wind speed and fetch. Yet the lake's enclosed nature means energy reflects and interacts within basin boundaries. Waves can build faster than anticipated if wind direction aligns with the longest axis of a lake. The temperature differential also influences lake effect precipitation. As cold air moves across the relatively warm water, it absorbs moisture. Downwind communities may receive intense snow bands. Visibility along shorelines drops quickly. For vessels operating offshore, this precipitation reduces visual cues further. There is also a psychological element to November. By late autumn, the sense of summer safety has faded. The water looks darker. The sky sits lower. The lake's surface takes on a steel grey tone. Even so, there are calm November days. This variability contributes to risk. A mild early November afternoon may encourage late-season outings. Forecasts may predict moderate winds, but if a low-pressure system deepens faster than expected, conditions can escalate within hours. The energy stored in the lake amplifies what would otherwise be a routine weather system. The Witch of November is not a singular storm each year. It is a pattern. It represents the intersection of seasonal transition and basin-scale physics. Cold air masses grow stronger. Lake water retains warmth. Pressure systems intensify. The result is wind over vast freshwater expanses at a time when temperatures hover near freezing. Cold water magnifies consequences. Anyone entering the lake during November faces immediate cold shock. Water temperatures often sit in the 40s or lower. Survival windows shrink dramatically. Combined with heavy seas and freezing spray, rescue becomes difficult. Harbours during November storms tell their own story. Boats secured at docks strain against lines. Waves surge into marina entrances. Water levels rise temporarily as wind pushes surface water toward shore. Lighthouses stand against white spray. Breakwalls disappear under crashing waves. It is easy to see why generations of mariners personified these storms. Naming them gives shape to something that feels deliberate, even though it is not. The witch does not choose victims. It emerges from gradients of temperature and pressure interacting over glacial basins carved thousands of years ago. As climate patterns shift, some research suggests that Great Lakes storms may change in frequency or intensity. Warmer overall lake temperatures can alter how much heat transfers into autumn air masses. Changing wind patterns influence fetch direction and storm tracks. What remains constant is the capacity for late-season storms to build rapidly and sustain force. For coastal communities, preparation is routine. Storm windows are installed. Boats are hauled early. Forecasts are monitored closely. For those unfamiliar with the region, the scale of November gales can be surprising. A freshwater lake generating 20-foot waves seems counterintuitive until one considers fetch length, basin depth, and atmospheric dynamics. Standing on a shoreline in early November, watching dark clouds gather over a steel grey horizon, it becomes clear that the lakes do not quiet gently into winter. They transition through a period of heightened volatility. And when those storms pass and temperatures drop further, the surface may begin to freeze along edges, introducing a different kind of hazard altogether, one that appears solid and stable, but moves in ways that are just as unpredictable as wind-driven water. When the wind finally loosens its grip and the deep autumn storms exhaust themselves, the Great Lakes do not immediately become calm in the way smaller lakes do. Instead, they begin another transformation. As air temperatures drop steadily below freezing, the surface along sheltered bays and shorelines starts to harden. Thin sheets of ice form first in quiet coves. Overnight, these sheets thicken. Snow dusts their surface. From a distance, it can look peaceful, smooth, still. The water that roared in November now appears solid, but ice on the Great Lakes does not behave like a frozen pond in a backyard park. It moves, it shifts, it fractures, it stacks, it grinds against itself and against shorelines with a force that surprises anyone who assumes frozen water is inert. Ice formation on large lakes is uneven from the beginning. Because of their size and depth, the Great Lakes do not freeze uniformly. Lake Superior, with its immense volume, may only partially freeze during milder winters. Lake Erie, being shallower, often develops more complete ice cover. Wind exposure, current flow, and depth variations create a patchwork. Thin ice can form quickly during calm, cold nights, but sustained wind prevents uniform freezing. When wind blows across partially frozen water, it pushes loose ice sheets together. They collide, they overlap, they pile upward into ridges known as pressure ridges. These ridges can rise several feet above the surface and extend downward below it. To someone standing on shore, the ice field may look like a flat white plain interrupted by low uneven ridges. But those ridges are evidence of force. Ice is not passive, it is responding to wind and current beneath it. Large sheets can drift miles from where they formed. Wind acts on the exposed surface of ice, pushing it across the water like a massive raft. Currents beneath continue moving as well. When wind direction shifts, ice sheets shift with it. The movement can be slow or abrupt depending on wind strength. This is where the phrase "moves like stone" becomes relevant. When ice packs compress against one another under strong wind, the pressure can be immense. The force exerted by large sheets grinding together can damage docks, piers, and shoreline structures. Ice is rigid, but it's not fragile in large masses. A single person stepping onto ice near shore may assume stability because it feels firm underfoot, but the sheet they're standing on may be attached loosely to a much larger floating mass. If wind increases, that entire section can begin drifting away from shore. Each winter there are reports of anglers or explorers stranded on drifting ice sheets. They walked out when conditions appeared stable. Hours later, wind shifted, and the ice separated from land, carrying them outward. From above, the separation may look gradual. A narrow channel of open water appears between shore and ice. But once that gap widens, returning becomes impossible without assistance. Rescue operations in such conditions are complex. Cold water, shifting ice, and unstable edges create hazards for both those stranded and those attempting to retrieve them. Ice thickness is not uniform even within a single sheet. Areas above deeper water may freeze more slowly. Currents flowing beneath certain sections thin the ice from below. River mouths, underwater springs, and wind-driven currents create variable thickness. Snow accumulation further complicates assessment. Snow insulates ice, slowing additional freezing beneath it. It also obscures cracks and thin areas. A surface that appears solid and white may conceal weaker sections underneath. Vehicles driving onto ice during winter add another risk dimension. On certain parts of the Great Lakes, especially Lake Erie and Lake Winnebago in nearby regions, ice fishing communities form temporarily on thick ice. But these activities rely on careful thickness measurement. Even then, sudden wind events can destabilize ice fields. Large sheets can fracture along pressure lines and begin drifting en masse. Once separated, the mass behaves like a floating platform. Waves beneath ice do not cease entirely. In areas of partial ice cover, open water sections still generate wave motion during wind events. These waves strike ice edges, breaking off chunks and pushing them inland or outward. The collision of moving ice blocks produces sounds that resemble distant thunder or grinding stone. The sound is a reminder that the lake beneath remains active. In early spring, as temperatures rise, melting does not occur evenly. Sunlight weakens ice from above, warmer water thins it from below, wind fractures it into flows. These flows drift, collide, and stack unpredictably. Shoreline ice shelves can form during winter when waves push water onto the beach, where it freezes layer upon layer. These shelves may extend outward from land, creating what looks like solid ground. But beneath those shelves, water often continues moving. Waves erode the underside, leaving hollow cavities. A person walking on such a shelf may be standing above open water without realizing it. When a shelf collapses, the fall can be abrupt. Even when lakes freeze extensively, complete stillness rarely lasts long. Wind across a frozen lake does not lose influence. It pushes ice sheets across the surface. The friction between ice and water below is relatively low. Large masses shift together. This movement exerts force on anything in their path. Shoreline structures built to withstand waves may not be designed to withstand horizontal ice pressure. Docks bend. Retaining walls crack. Boat lifts become twisted under shifting weight. The thickness of ice required to support a person differs significantly from that required to support a vehicle. General safety guidelines often suggest that 4 inches of clear solid ice may support a person, while 8 to 12 inches may support a small vehicle. But these numbers assume consistent thickness and clear conditions. On the Great Lakes, thickness varies across short distances. Clear ice is stronger than snow ice, which forms when slush refreezes. Snow ice may look solid but contains trapped air pockets that reduce strength. Currents beneath the ice continue to move water from one basin to another through connecting straits and rivers. The Straits of Mackinac, linking Lake Michigan and Lake Huron, rarely freeze completely due to strong currents. Ice may form and break repeatedly there throughout winter. This creates additional unpredictability. Large flows can accumulate temporarily in these connecting channels, only to break apart under shifting wind. From a distance, a frozen lake may appear calm and permanent, but unlike a small inland pond, its frozen surface sits atop vast moving water. Temperature fluctuations also matter. Winter thaws weaken ice quickly. A few days of above freezing temperatures can reduce thickness significantly, especially when combined with rainfall. Rainwater pooled atop ice accelerates melting from above while water below continues thinning it from beneath. The result can be a deceptively solid-looking surface that is structurally compromised. Rescue statistics during winter months reflect these dynamics. Individuals venturing onto ice without measuring thickness or considering recent wind and temperature changes account for many incidents. Ice anglers drifting offshore on broken sheets require helicopter retrieval. Snowmobilers encountering thin patches face sudden immersion. Cold water immersion in winter is even more severe than during autumn storms. Water temperatures hover near freezing. Survival time without protective gear may be measured in minutes. Even wearing winter clothing does not guarantee buoyancy. Heavy coats and boots absorb water quickly, increasing weight and reducing mobility. Ice also changes wave dynamics when storms strike partially frozen lakes. During strong wind events, open water areas generate waves that collide with ice edges. The impact fractures ice further. Broken chunks pile along shorelines in thick heaps known as ice shoves. These shoves can extend several feet high, pushing inland onto beaches and sometimes into yards or structures. The force required to move such masses is substantial. Wind across a broad frozen surface exerts consistent pressure. Ice fields behave like slow-moving continents on a smaller scale. There are winters when ice cover remains minimal due to warmer conditions. In those years, wave action continues throughout the season, contributing to shoreline erosion. In colder winters with extensive ice cover, wave erosion may decrease temporarily. But the mechanical force of shifting ice introduces its own form of shoreline stress. The Great Lakes do not enter a dormant phase in winter. They shift from liquid motion to solid motion, but motion remains constant. For those living along the shoreline, winter becomes a season of monitoring rather than ignoring the water. Cracks appear where none existed days before. Sheets separate from land overnight. Pressure ridges grow along certain sections while others remain flat. The myth of stability returns in winter in a different form. Frozen water looks reliable. It reflects light differently than liquid. It does not ripple. It appears fixed. But beneath that surface, currents continue flowing. Wind continues pushing. Temperature continues fluctuating. And when spring approaches, melting does not simply reverse the process quietly. Ice breaks apart unevenly. Flows drift and collide. Open water expands unpredictably. The lake transitions again, not gently, but through fragmentation and movement. As the last sheets dissolve and liquid water dominates once more, the lake may appear calmer than during the storms of November or the shifting ice of January. Yet beneath that calm surface, the same forces of depth, temperature gradient, and stored energy remain ready to reassert themselves as the seasons cycle forward, influenced increasingly by broader climate patterns that are beginning to reshape how these freshwater seas behave year after year. For most of human history, crossing the Great Lakes required judgment sharpened by experience and a tolerance for uncertainty. Mariners watched the sky. They read barometers. They studied cloud formations and wind shifts. A falling pressure needle meant caution. A sudden wind veer meant change. Today, technology surrounds the lakes. Satellites track storm systems days in advance. Radar sweeps the basin continuously. Buoys anchored offshore transmit real-time data about wind speed, wave height, and water temperature. GPS units plot precise positions down to a few meters. Radar overlays reveal nearby vessels even in fog. On paper, it appears that the element of surprise should be gone, and yet the Great Lakes continue to challenge both seasoned captains and casual boaters. Technology does not remove physics, it only informs us about it. Marine forecasts for the lakes are detailed. They provide predicted wind speeds, wave heights, and wave periods. They distinguish between nearshore waters and open waters. They issue small craft advisories, gale warnings, and storm warnings. But forecasts are models. They are built from data and probability. While accuracy has improved dramatically over the past decades, localized conditions can still diverge from predicted averages. A forecast of 4 to 6 foot waves does not mean every wave will be exactly that height. It represents a statistical average. Individual crests may be higher. Interference patterns may create occasional larger waves. A recreational boater glancing at a single number may underestimate what 6 feet means in short-period freshwater waves. Radar and GPS reduce navigation errors significantly. In heavy fog, vessels equipped with radar can detect other ships and shoreline contours. GPS eliminates much of the guesswork involved in dead reckoning. Electronic chart plotters display detailed lake floor maps, highlighting shoals and hazards. Yet reliance on electronics introduces its own vulnerabilities. Power systems can fail, batteries can drain, screens can malfunction in extreme cold, software requires updates, signals can be lost temporarily. Even when devices function perfectly, interpretation matters. Reading a radar display requires training. Distinguishing between wave clutter and actual objects takes experience. GPS coordinates provide position, but they do not automatically account for drift due to wind and current unless the operator actively compensates. On small recreational craft, technology may be minimal. Many boats operating near shore rely primarily on visual navigation and smartphone weather apps. While mobile technology provides convenient access to forecasts, cellular coverage is not uniform across all portions of the lakes. Offshore, signal strength can drop. Data updates may lag. There is also a psychological shift that technology creates. When a device provides a precise reading, it can inspire confidence. Our 8 feet high does not reduce their 8 feet high does not reduce their force against a hull. Large commercial freighters on the Great Lakes integrate sophisticated navigation systems. They use automatic identification systems, AIS, to broadcast their position and receive the positions of other vessels. They track real-time meteorological data. They coordinate with traffic management services in narrow channels. Even so, captains still alter routes to avoid the worst of autumn storms. They reduce speed in heavy seas. They make judgment calls beyond what screens display. Technology informs decisions. It does not make them. Rescue operations have benefited enormously from modern tools. Coast Guard helicopters equipped with infrared imaging can locate vessels in distress even in poor visibility. Emergency position, indicating radio beacons, EPIRBs, transmit distress signals via satellite, dramatically reducing search areas. These advancements have saved lives that might have been lost in previous decades. However, distress signals often activate only after a vessel has already encountered severe trouble. Cold water immersion time remains governed by temperature, not signal strength. There is also the matter of overconfidence. With reliable engines, reinforced hulls, and accurate forecasts, some boaters may venture out in marginal conditions, believing they can rely on equipment if weather worsens, but mechanical systems can fail under stress. Fuel lines clog, steering systems jam, sails tear, electrical systems short out under heavy spray. In steep, short-period waves, even well-maintained vessels face strain. The lake's freshwater environment introduces specific technical considerations as well. Freshwater is less corrosive than saltwater, which reduces some forms of structural degradation. However, cold temperatures can affect fuel viscosity and battery performance. Freezing spray can encase antennae and sensors in ice, impairing signal transmission. Radar screens do not prevent ice from accumulating on deck. In winter operations, even large ships must monitor icing carefully. Crew members sometimes manually remove ice buildup to maintain stability. Underwater technology has also advanced. Sonar mapping has revealed detailed images of shipwrecks resting at depth. Remote-operated vehicles explore areas too deep or dangerous for divers. Hydrographic surveys continually update charts. These tools increase knowledge of the lake floor. They help avoid grounding incidents that were common in earlier centuries. Yet shifting sandbars and sediment deposits still alter shallow areas over time. Charts are updated periodically, but storms can reshape certain nearshore features within a single season. Climate monitoring adds another technological layer. Scientists deploy sensor arrays to track temperature profiles, ice cover extent, and evaporation rates. Long-term data sets help researchers understand how warming trends may alter storm intensity or lake levels. These insights inform policy and infrastructure planning. Still, the day-to-day experience of wind-driven waves remains immediate. A smartphone alert indicating a sudden wind advisory may appear while someone is already offshore. The alert does not change the waves already building. Human interpretation sits between technology and outcome. Weather apps display wind direction arrows and speed numbers, but understanding how a northwest wind across Lake Michigan builds waves toward the southeast shoreline requires spatial awareness. A reading of 25 miles per hour may not seem alarming to someone accustomed to inland breezes. Over 200 miles of open water, that wind generates significantly more energy. Navigation systems may provide exact headings, but if wind and current push sideways, maintaining that heading requires compensation. On open water without visible landmarks, small steering errors accumulate quickly. GPS tracks may show a curved path when the intention was straight. There are also moments when technology conflicts with instinct. A forecast may indicate safe conditions for several hours. Dark clouds on the horizon may suggest otherwise. Deciding whether to trust the screen or the sky becomes a personal judgment. The most experienced mariners tend to integrate both. They read instruments and observe environmental cues. They watch how wave patterns change, how cloud bases lower, how barometric pressure trends over time. Technology extends awareness but does not replace experience. The lakes have always responded to gradients of pressure, temperature, and wind. That has not changed. What has changed is the speed at which information travels. Storm systems are now tracked continuously. Warnings are broadcast instantly. Search areas narrow faster during emergencies. These advancements reduce uncertainty, but they do not eliminate hazard. Standing on shore, watching a large freighter glide across Lake Superior under clear skies, It is easy to believe that engineering has mastered the environment, yet that vessel's captain is reading forecast carefully, adjusting speed based on wave period and preparing for possible shifts hours before they are visible. Technology meets fresh water at the point of decision-making. It provides numbers, images, and alerts. The water responds only to physical law, and as climate patterns evolve, with warmer lake surfaces in some years and altered wind patterns in others, the relationship between data and reality may grow more complex, requiring even closer attention to how these inland seas are changing in ways that extend beyond a single forecast or season. Interruption. If the air is crisp and visibility high, that line can feel almost architectural, like a boundary carefully drawn with a ruler. Your brain processes that scene in a very specific way. Humans evolved in landscapes filled with trees, hills, and varied terrain. Most of our depth perception relies on landmarks. We judge distance by comparing objects against one another, a house against a hill, a person against a tree, a car against a building. On the Great Lakes, those reference points disappear. The horizon offers no scale. Without visible markers, the brain compresses distance. 20 miles can look like 2. A freighter halfway across the basin can appear close enough to touch. The far shore, when faintly visible, may look deceptively reachable. This compression influences behaviour. People are more likely to attempt long swims, extended paddle trips, or casual crossings when the visual field feels manageable. The water looks flat. The sky looks open. There is no obvious barrier signalling risk. The term lake reinforces this mental framing. When someone hears ocean, they imagine tides, sharks, and crashing surf. When they hear lake, they imagine fishing docks and quiet coves. Language shapes expectation before a single wave is observed. The Great Lakes occupy a category that confuses instinct. They look like oceans in scale, but carry the cultural label of lakes. That mismatch lowers perceived threat. Psychologists describe this phenomenon as risk normalization. When a setting appears familiar or domestic, individuals unconsciously downgrade hazard assessment. Beaches along Lake Erie or Lake Huron often have picnic tables, restrooms, paved walkways, and lifeguard chairs. These cues signal organisation and safety. The environment feels curated. But infrastructure does not alter wave period, water temperature, or current strength. Another psychological factor is repetition. Millions of people visit Great Lakes beaches every year without incident. They wade, swim, paddle, and boat successfully. Each safe experience reinforces the belief that the environment is manageable. When an individual has entered the water multiple times without encountering rip currents or severe cold shock, they may begin to assume that those risks are rare or exaggerated. Familiarity reduces caution. This effect is amplified on calm days. A glassy surface and gentle breeze create visual reassurance. The brain reads smooth water as stable. Small ripples appear harmless. It is difficult to imagine that within hours that same surface could support steep, closely spaced waves. Human perception tends to overweight immediate conditions and underweight potential change. Distance distortion plays a role in offshore incidents. Without visible land ahead, boaters may feel closer to shore than they are. GPS units provide precise coordinates, but many recreational boaters glance at screens only occasionally. When the horizon appears near, urgency decreases. On clear days, the opposite shore of Lake Michigan may be visible faintly as a dark line. The brain interprets that faint line as reachable, but crossing the lake can require hours of sustained travel under stable conditions. If weather shifts mid-crossing, returning to either shore may involve similar distances. There is also a cognitive bias known as optimism bias. People generally believe that negative events are less likely to happen to them compared to others. News of shipwrecks or drownings may be processed as distant stories, relevant to other individuals in different circumstances. A swimmer entering the water during moderate surf may acknowledge that rip currents exist, but assume they will recognise and avoid them. A boater launching under building clouds may believe that mechanical reliability or personal skill will compensate for changing weather. The Great Lakes' aesthetic qualities intensify this bias. Sunsets over Lake Superior are dramatic. Morning mist over Lake Ontario appears peaceful. The visual beauty encourages emotional attachment. People return repeatedly to these shores for recreation and reflection. Emotional attachment can soften risk perception. When a place feels familiar and meaningful, acknowledging its danger becomes psychologically uncomfortable. It is easier to frame incidents as anomalies rather than inherent possibilities. Group dynamics further influence decisions. When multiple people enter the water together, individual hesitation decreases. Social proof suggests that if others are swimming, conditions must be acceptable. Even on days when lifeguards post yellow or red flags indicating moderate to high hazard, beachgoers may interpret those warnings as overly cautious if they see others in the water. The absence of visible turbulence reinforces this dismissal. Rip currents are often invisible from standing height. Longshore currents move quietly. Cold water lurks beneath a thin, warm surface layer. The brain relies heavily on visual cues. When cues are subtle or absent, risk assessment falters. There is also the effect of scale invisibility offshore. On the open lake, with no land in sight, the environment can feel infinite. Some individuals experience mild spatial disorientation even in calm conditions. The absence of boundaries removes orientation anchors. In such settings, judgment may shift from analytical to instinctive. When fog reduces visibility, the horizon disappears entirely. Without that line separating sky and water, up and forward can blur psychologically. The lake feels smaller yet more isolating simultaneously. The mind struggles with environments that lack edges. Another psychological element is temporal distortion. On calm water, time may feel slower. Paddling across smooth surface seems effortless. A short excursion may gradually extend beyond planned limits, without the participant realizing how far they have travelled. Fatigue builds gradually. By the time someone decides to return, wind direction may have shifted, turning a relaxed outward paddle into a strenuous return against chop. The horizon's flatness masks distance and effort. Risk perception also interacts with seasonal familiarity. In summer, when beaches are crowded and lifeguards present, individuals may assume oversight extends beyond visible patrol zones. In autumn, when beaches empty, the absence of crowds can create a false sense of exclusivity rather than caution. A quiet shoreline in October may look peaceful rather than hazardous, even as water temperature drops significantly. Media portrayal influences psychology as well. Ocean disasters often receive dramatic coverage. Images of hurricanes and storm surges dominate headlines. Great Lakes incidents, though serious, may receive more regional attention. Without national spotlight, the lake's capacity for severe conditions may remain underappreciated by those outside the region. Even within the region, daily exposure to the lake's presence normalizes their scale. Residents may drive along shorelines routinely without incident. The water becomes background scenery. That familiarity reduces perceived volatility. Training and education shift perception. Sailors who study wave period and fetch understand how quickly conditions can build. Lifeguards trained to spot rip currents view the shoreline differently from casual swimmers. Experience recalibrates intuition. The psychology of the horizon is therefore a study in contrast. Visually, the lakes appear approachable. Emotionally, they feel familiar. Linguistically, they are labelled as lakes, not seas. Physically, they operate at scales comparable to inland oceans. Recognizing this duality is not about fear. It is about aligning mental models with physical reality. When the brain understands that a flat horizon hides hundreds of miles of fetch, that a calm surface may overlay 40-degree water, and that a familiar beach can host powerful currents, behaviour adjusts accordingly. Life jackets become routine rather than optional. Forecast checks become habitual. Entry points are chosen carefully. The horizon remains beautiful. The sunsets remain dramatic. But beneath that straight line lies depth, cold, current and wind energy accumulated across glacial basins. And as climate trends alter lake temperatures and wind patterns over longer timescales, even that familiar horizon may begin to behave in subtly different ways than it did decades ago, reshaping the balance between perception and reality once again. Beneath you, on Lake Superior, the bottom beneath you. On Lake Superior, the bottom can lie more than 1,300 feet below the surface. On Lake Michigan and Lake Huron, depths exceed 900 feet in places. Even Lake Ontario reaches beyond 800 feet. These are not shallow inland waters. They are vertical spaces large enough to swallow skyscrapers. But depth does not announce itself visually. Water reflects light. It conceals what lies beneath a thin surface layer. When you look out across the lake, your brain reads width easily. It struggles with vertical scale. There is no visual cue for how far down the bottom sits. This invisibility changes perception. Standing on shore, you see horizontal vastness. You do not sense vertical magnitude. Yet depth influences nearly everything about how these lakes behave, from temperature stability to wave formation to preservation of shipwrecks. Darkness begins only a few feet below the surface. Light penetration in freshwater varies depending on clarity and suspended particles. In some areas, particularly parts of Lake Superior, water can be remarkably clear. Even so, sunlight fades quickly with depth. Beyond a certain point, the lake becomes dim. Farther still, it becomes black. Divers descending along anchor lines often describe the sensation of entering a space where surface brightness disappears rapidly. Even during daytime at sufficient depth, artificial lights become necessary. That darkness is not empty. It contains cold water layers, thermoclines, and in some cases, intact wrecks resting undisturbed for decades or centuries. The combination of depth and cold preserves. In saltwater oceans, shipwrecks degrade faster due to corrosion and marine organisms. In the Great Lakes, cold freshwater slows those processes. Wooden hulls remain recognizable. Painted lettering sometimes persists, but reaching those wrecks requires descending through temperature layers and pressure changes. Pressure increases with depth. At 33 feet underwater, pressure doubles compared to the surface. At 66 feet, it triples. Deep technical dives on the Great Lakes require specialized training and equipment due to depth alone. Most recreational divers remain within safer limits, yet even moderate depths can bring rapid temperature drops. Thermoclines create sharp boundaries between warmer surface water and colder deep water. Passing through one can feel like entering a different season instantly. This layering affects sound as well. Sound travels differently in water than in air. In fact, it travels faster, roughly 4 times faster in freshwater compared to air. That speed, combined with temperature layers, bends and refracts sound waves in complex ways. On the surface, foghorns can seem closer or farther than they truly are. Underwater, engine noise travels long distances. Divers sometimes report hearing distant boat engines clearly even when the vessels themselves are not visible from below. Sound distortion contributes to disorientation. Because sound travels faster and reflects off the lake bottom and thermoclines, locating its source becomes difficult. A noise heard to the right may originate from a vessel ahead or behind. On open water in fog, this can create confusion. Darkness and depth also influence human psychology directly. Humans are surface-oriented creatures. We evolved walking on land where depth is limited to caves and valleys. Open vertical water space triggers a different sensory response. Swimming over deep water feels different from swimming over shallow sand. Even if the depth difference is invisible, knowing that hundreds of feet lie below can alter comfort levels. Some swimmers experience mild anxiety when crossing from visible bottom to open depth. This reaction is not irrational. It is a response to uncertainty. depth means distance from solid ground. It means that if something goes wrong, reaching bottom for leverage is impossible. For boaters, depth influences anchoring decisions. In shallower bays, anchoring may be straightforward. In deeper offshore areas, anchor lines must be significantly longer to hold properly. Misjudging depth can result in dragging anchor during building wind. The Great Lakes' depth also affects thermal stability. Because deep water retains cold year-round, it moderates surface temperature changes. Even after extended warm periods, deeper layers remain cold. When storms mix these layers upward, surface temperatures can drop rapidly. The depth stores energy and cold simultaneously. Darkness at depth also affects rescue and recovery. In the event of a sinking or accidental fall overboard, locating objects or individuals beneath the surface becomes exponentially more difficult as depth increases. Even with modern sonar, searching vast deep areas requires time and precision. Lake Superior alone contains enough water to cover North and South America under a foot of water. That volume creates an environment where scale challenges search efforts. Night compounds these factors. When darkness falls over open water, visual cues disappear almost entirely. Shoreline lights may be visible from certain angles, but orientation becomes dependent on instrumentation. Moonlight reflecting off waves can create visual illusions. Whitecaps may blend into the surrounding surface. Estimating wave height becomes harder. Sound becomes more prominent at night. The slap of water against hulls, the hum of engines in the distance, the low echo of foghorns. Without visual anchors, these sounds feel amplified. In heavy weather at night, depth becomes abstract yet present. A vessel rising and falling in the steep waves does so above hundreds of feet of water. That vertical space adds psychological weight. The Great Lakes are often described as inland seas not only because of their width, but because of their depth and behaviour. Ocean sailors recognise similar feelings offshore, the sense of floating above vast unseen volume. The difference here is freshwater and enclosure. The bottom is closer than in many oceanic trenches, yet still far beyond human reach without specialised equipment. Submersible explorations have revealed remarkably intact wrecks resting upright in cold darkness. These discoveries reinforce how depth preserves history, but they also highlight how quickly light and warmth fade beneath the surface. Cold water absorbs heat. Darkness absorbs light. Pressure increases steadily. For those operating on the surface, these factors remain hidden but influential. A swimmer floating in calm water may not think about the temperature at 100 feet below. A kayaker crossing open water may not consider how sound carries across thermoclines. Yet depth shapes the system's behaviour constantly. When wind transfers energy to water, the depth determines how that energy propagates. In deeper lakes, waves can grow larger before bottom friction slows them. In shallower sections, waves steepen faster. The unseen vertical dimension affects the visible horizontal motion. Sound, depth, and darkness combine into an environment that feels simple from shore and complex from within. Lakes appear flat from above. Beneath that flatness lies layered water, pressure gradients, preserved wrecks, and acoustic distortions. Standing at the shoreline at night, looking out over black water that reflects faint starlight, it is easy to underestimate how much space lies below that surface. But the Great Lakes are three-dimensional systems. They move not only across their surfaces but within their depths, and as environmental conditions shift over decades, with warming trends altering temperature layers and ice cover patterns, even the structure of that depth-driven behaviour may change, influencing storms, currents, and seasonal cycles in ways that extend beyond what is immediately visible from the shore. For most of recorded history, the Great Lakes have followed recognisable seasonal patterns. Winter brought ice, spring brought rising water from snowmelt, summer brought stratified layers and warmer surface temperatures, autumn brought powerful storms driven by cold air crossing relatively warm water. The details varied year to year, but the structure felt stable. That structure is beginning to shift. The Great Lakes region has experienced measurable warming over the past several decades. Average air temperatures have risen, ice cover duration has generally decreased. Surface water temperatures in several lakes have trended upward, particularly in summer. At first glance, warmer water might sound less threatening. Longer swimming seasons, reduced ice hazards, milder winters, but warming alters energy balance. When surface water temperatures rise, more heat becomes available for transfer into the atmosphere during autumn. That additional heat can influence storm development. Warmer lake surfaces can intensify low-pressure systems moving across the basin. A warmer lake does not necessarily mean calmer conditions. In some years, reduced ice cover during winter allows wind to interact directly with open water for longer periods. Ice traditionally dampens wave action by acting as a barrier between wind and water. With less ice, winter storms can generate waves that would previously have been suppressed. Shoreline erosion may increase under such conditions. Higher evaporation rates also accompany warmer surface temperatures. The Great Lakes lose significant water volume through evaporation each year. Changes in temperature and wind patterns influence how much water leaves the basin. Lake levels fluctuate naturally, but climate trends may amplify those fluctuations. Periods of unusually high water levels strain coastal infrastructure. Docks submerge, erosion accelerates. Combined with strong storms, elevated water increases wave impact against bluffs and retaining walls. Conversely, prolonged low water periods create different hazards. Shoals become more exposed. Navigation channels require more dredging. Harbours may become less accessible for larger vessels. The unpredictability arises from variability layered on top of long-term trends. Some years bring record high water levels, others bring sharp declines. Rapid transitions between extremes challenge planning and risk assessment. Storm patterns are also shifting. Research indicates that heavy precipitation events in the Great Lakes region have increased in frequency. More intense rainfall contributes to runoff surges from surrounding watersheds. River inflows carrying sediment and debris into the lakes can alter near-shore conditions quickly. Strong runoff following storms influences currents and water clarity. Warmer air can hold more moisture. When storm systems form over warmer lakes, the potential for heavy rainfall increases. Combined with strong winds, these storms can create compound hazards: elevated waves, strong currents, reduced visibility, and rapidly changing water levels. Lake effect snow patterns are evolving as well. With less consistent ice cover, open water in winter provides moisture to cold air masses longer into the season. This can intensify lake effect snowfall in downwind areas during certain conditions. At the same time, milder winters may shorten overall ice duration. The interplay between warming trends and episodic cold outbreaks creates variability. Some winters may still produce extensive ice cover. Others may see large areas remain open. For communities accustomed to relatively predictable freeze and thaw cycles, this inconsistency complicates preparation. Warming also influences stratification timing. Surface waters warm earlier in spring and may remain warm later into autumn. The seasonal turnover process, when water layers mix and redistribute oxygen and nutrients, may shift in timing or intensity. Changes in mixing patterns affect not only ecosystems, but also temperature distribution near shore. Unexpected cold upwelling events may become more noticeable when surface temperatures are higher overall. The contrast between warm air and suddenly cold nearshore water can be jarring. For swimmers, these temperature swings create additional unpredictability. What felt safe and comfortable one week may feel sharply colder the next due to wind-driven mixing. Wind patterns themselves may shift. Climate models suggest changes in jet stream behaviour and regional pressure systems. If prevailing wind directions change even slightly, fetch patterns across elongated lakes such as Michigan and Huron shift as well. Different shorelines may experience increased wave exposure compared to historical norms. Communities that rarely faced direct wave energy in past decades may encounter more frequent erosion events. Infrastructure built under older assumptions about water levels and storm frequency may face stress. Harbour designs, breakwalls and shoreline reinforcements rely on historical data sets. If extremes become more common, those designs may require re-evaluation. There is also the issue of algal blooms. Warmer surface temperatures combined with nutrient runoff from heavy rainfall create conditions favourable for harmful algal growth, particularly in Lake Erie. While algal blooms are primarily ecological concerns, they influence water quality and recreational safety. Reduced water clarity changes how swimmers perceive depth. Surface scum can mask underlying currents. The lakes remain freshwater systems shaped by glacial basins, but the climate envelope around them is shifting. This does not mean that every year will be more extreme than the last. Climate change often manifests as increased variability. Unseasonably warm stretches followed by abrupt cold snaps. Record high water levels followed by sudden drops. Storms that intensify faster than expected due to warmer underlying water. For mariners, this variability complicates planning. Historical experience remains valuable, but patterns may not repeat exactly as they once did. A harbour that was typically protected under certain wind conditions may now experience different exposure if prevailing wind angles shift. Search and rescue operations must account for changing water temperatures as well. If surface waters warm earlier in the year, recreational use increases sooner. Cold water incidents may occur during transitional periods when air feels warm but deeper layers remain cold. Data collection across the Great Lakes has expanded significantly. Buoys monitor temperature at multiple depths. Satellites track surface temperature anomalies. Ice cover is measured annually. These data sets help researchers identify trends and refine models. But translating long-term climate data into day-to-day safety decisions requires public awareness. The phrase new unpredictability reflects not chaos but complexity. The lakes have always been dynamic. What is changing is the baseline around which that dynamism occurs. Warmer average temperatures alter storm fuel. Reduced ice alters winter wave exposure. Shifting precipitation alters runoff and current patterns. For someone standing on a shoreline, these changes may not be immediately obvious. The horizon still appears straight. Waves still roll toward land. Fog still forms under certain conditions. Yet the frequency and intensity of specific events may gradually differ from what previous generations experienced. Understanding this requires flexibility. Risk assessment cannot rely solely on memory of how conditions behaved decades ago. It must incorporate updated data and evolving patterns. Technology plays a role in tracking these changes. Education plays a role in interpreting them. The lakes are not becoming entirely unfamiliar. They remain governed by physics. Wind transfers energy to water. Cold extracts heat from the body. Currents move along contours carved by ice. But the context within which those processes unfold is adjusting. And as variability increases, the margin between calm and severe conditions may narrow in ways that demand quicker responses and more attentive planning, particularly when emergencies arise and the window for effective rescue remains defined by temperature, distance and time rather than intention. When something goes wrong on the Great Lakes, the response begins quickly. Distress calls are monitored, coordinates are relayed, rescue stations activate, helicopters prepare for launch, cutters leave harbour. The system is organised, practised and equipped with modern tools. And yet, even with preparation and technology, rescue on the Great Lakes is often extremely difficult. The difficulty begins with scale. Lake Superior alone spans more than 31,000 square miles. Lake Michigan stretches over 300 miles from north to south. When someone goes missing offshore, the search area expands rapidly. Wind moves objects. Currents shift positions. Waves obscure visibility. Even if a distress signal provides an exact location at the moment of transmission, that location begins changing immediately afterward. A person in the water drifts according to surface wind, wave direction, and underlying current. That drift may not be straight. It may curve or shift as wind patterns change. Rescue coordinators calculate projected drift zones using wind speed, direction, and water movement data. But those calculations involve estimates. If a distress signal is delayed, the uncertainty increases. Time is the second major factor. Cold water drastically limits survival windows. In water below 50 degrees Fahrenheit, muscle strength declines quickly. Hypothermia can develop within an hour. In near-freezing water, unconsciousness may occur in minutes. Search aircraft may take time to reach offshore coordinates, especially during severe weather. Helicopters cannot always fly in extreme wind or heavy icing conditions. Rescue boats cannot always operate safely in towering waves. When storms are at their worst, rescue may need to wait for brief windows of relative improvement. That waiting compresses the survival window further. Visibility compounds the problem. Fog reduces aerial search effectiveness. Heavy rain obscures surface details. At night, locating a person in the water becomes exponentially harder. A human head in waves is small relative to the surrounding surface. Whitecaps blend with foam. Dark clothing blends with shadow. Search teams rely on visual scanning from aircraft and vessels. Even with infrared technology, cold water equalizes temperatures quickly, reducing contrast. Distance from shore affects response time. Many incidents occur near beaches, but others happen miles offshore. Recreational boaters sometimes travel farther than intended. Sailboats crossing open water may be hours from harbour. If a vessel capsizes 20 miles offshore during building weather, reaching that location requires navigating the same rough conditions that caused the incident. Large rescue cutters are built for heavy seas, but even they experience limitations in extreme wave heights. Small rescue boats may not be deployable in severe surf near shore. Lifeguards at beaches face similar constraints. During high-hazard conditions, entering turbulent water may endanger rescuers as well. Coordination across jurisdictions adds complexity. The Great Lakes are shared between the United States and Canada. Cross-border coordination functions effectively, but communication protocols must align. Jurisdictional boundaries require clarity during emergencies. Search grids may cross into international waters. Equipment limitations exist despite modernization. Rescue helicopters have fuel constraints. Time on station is limited. Pilots must account for wind and icing risk. Rescue swimmers entering cold water during hoist operations face their own exposure limits. In strong winds, hovering over waves requires precise control. Downwash from helicopter rotors interacts with wave tops, adding spray and instability. For vessels in distress, signalling effectiveness matters. Flares are visible only for brief moments. Emergency beacons depend on battery life and proper activation. Personal flotation devices increase survival time but do not guarantee visibility. Many recreational boaters underestimate the importance of wearing life jackets at all times. If someone falls overboard unexpectedly during rough conditions, the time available to retrieve them may be seconds before distance increases significantly. Man overboard drills emphasize immediate action for this reason. Cold shock further complicates rescue. A person entering cold water may inhale water during the gasp reflex. If unconsciousness occurs rapidly, they may submerge before rescuers arrive, even if response time is short. Search transitions from rescue to recovery quickly in cold water incidents. Depth adds another layer of difficulty. If a vessel sinks in deep water, locating the wreck requires sonar scanning. Recovery at depth may not be feasible or may take extended time. The preservation of wrecks in cold fresh water does not make them easier to locate initially. Underwater currents and sediment can obscure objects. Communication challenges arise during severe storms. Radio signals may be disrupted by interference or equipment damage. Antennas iced over during freezing spray events may transmit weakly. Distress calls sometimes break up mid-sentence due to power loss. In high wind, even holding a radio steady can be difficult on a pitching deck. Psychological stress during emergencies affects communication clarity. Callers may provide incomplete coordinates. Panic alters speech patterns. Dispatchers must extract precise information quickly while offering instruction. Meanwhile, wind continues pushing vessels and individuals off initial positions. Rescue along rocky shorelines presents unique hazards. When swimmers are caught in rip currents near piers or break walls during high surf, lifeguards and responders must navigate turbulent water and reflected waves. Rescuers risk being struck against structures or pulled into the same currents. Even when rescue is successful, medical stabilization becomes urgent. Hypothermia requires careful rewarming protocols. Sudden rewarming or rough handling can trigger cardiac complications in severe cases. Ambulances waiting on shore must be positioned for quick transfer. In winter, ice complicates access. When individuals drift on broken ice sheets, helicopters may be required for retrieval. Landing on unstable ice is impossible. Hoist operations over shifting flows require precise timing. Rescuers must monitor both wind and ice movements simultaneously. Search areas expand geometrically with time. If a person disappears without immediate distress signal, search begins based on last known position. Wind and current projections generate a search box. Hours later, that box enlarges. Aircraft may fly grid patterns across vast expanses of open water. In severe weather, even spotting debris becomes difficult. Waves hide objects between crests. Whitecaps create visual clutter. Reflections distort shape. The Great Lakes' size means that even well-resourced rescue operations cannot be everywhere at once. Stations are strategically located, but distances between them remain significant. For recreational users, the assumption that help is always close can be misleading. Help is available, but response time depends on conditions. Prevention therefore becomes critical. Checking marine forecasts before departure, wearing life jackets consistently, carrying functioning communication devices, filing float plans that outline intended routes and return times. These steps narrow the gap between incident and rescue. The lakes do not prevent rescue. They complicate it through scale, cold, wave energy, visibility limits, and distance. Even in calm weather, the expanse creates search challenges. In storms, those challenges multiply. Standing on shore watching a rescue helicopter pass overhead may give the impression of swift resolution. Often that helicopter is part of a coordinated effort involving multiple vessels, aircraft, dispatchers, and medical teams working against time and environmental force. Because once someone is in the water, especially in cold, wind-driven conditions, the clock begins running immediately, and the outcome depends not only on how quickly rescuers respond, but on how much preparation occurred before the emergency began, and whether the risks of wind, current, cold, and distance were recognized before the horizon ever began to change. After everything we've explored, the storms, the waves, the cold, the depth, the shifting ice, it would be easy to frame the Great Lakes as something hostile. But that would miss the point. The lakes are not aggressive. They are not waiting. They are not unpredictable in a mystical sense. They operate according to physics that is consistent and measurable. Wind transfers energy. Cold extracts heat. Currents redistribute water. Depth stores temperature. The danger appears when human expectation does not align with those processes. Fear tends to distort judgment in its own way. It can paralyze decision-making or lead to avoidance without understanding. Respect works differently. Respect begins with scale, recognizing that Lake Superior holds more water than all the other Great Lakes combined. Understanding that Lake Michigan stretches longer than some countries. Accepting that wave heights of 15 or 20 feet on freshwater are not exaggerations. Scale reframes behavior. A kayaker crossing a protected bay may do so confidently, while recognizing that open water crossings require additional planning. A swimmer may enjoy near-shore conditions while paying attention to posted hazard flags. Respect is practical. It looks like checking marine forecasts before departure, not just glancing at air temperature, but reading wind direction, sustained speeds, gust predictions, and wave period. It looks like noting that a northwest wind across a long fetch will build stronger waves on a southeastern shoreline hours later. Respect involves preparation. Wearing a life jacket even when the surface appears calm, carrying redundant communication tools, informing someone on shore of departure time and intended return. These are not signs of fear, they are acknowledgements of environment. The Great Lakes reward preparation. Sailors who understand wave period adjust speed accordingly. Anglers who monitor weather radar turn back before storms intensify. Beachgoers who recognize rip current conditions choose safer entry points. Respect also means understanding limits. Cold water does not negotiate with physical fitness. Even strong swimmers experience rapid heat loss. Knowing water temperature before entering changes choices. Respect extends to winter. Ice thickness is measured, not assumed. Snow cover is treated as insulation rather than proof of strength. Wind direction is considered before venturing far from shore on frozen surfaces. Communities along the lakes demonstrate this mindset seasonally. Boats are hauled before late autumn storms intensify. Shoreline properties are reinforced in anticipation of high water levels. Harbours monitor changing lake levels. Fear would imply avoidance. Respect implies engagement with awareness. The lakes provide transportation, recreation, drinking water, and economic connection for millions of people. They are central to regional identity. Sunrise paddles on glassy water, sailboats silhouetted against sunset, ice formations along winter shores. These experiences are not contradictions to hazard. They coexist with it. Understanding risk allows those experiences to continue safely. The phrase inland sea is often used to describe the Great Lakes. It captures both scale and behaviour. Seas demand navigation skill, weather awareness, and contingency planning. Treating the lakes as small ponds diminishes them. Treating them as oceans without tides but with oceanic potential reframes decisions. Education plays a significant role in cultivating respect. Rip current awareness campaigns reduce drownings. Cold water survival training teaches proper response to immersion. Boating courses emphasize weather interpretation and navigation. Knowledge reduces surprise. When a storm builds faster than expected, a prepared boater already has a plan for safe harbour. When fog rolls in, a prepared paddler knows how to maintain bearing. When water temperature is 48 degrees in May, a prepared swimmer recognises the risk of extended immersion. Respect also involves restraint, choosing not to launch when small craft advisories are active, postponing a crossing when forecasted winds align with maximum fetch, staying clear of piers during high surf. These choices are not admissions of weakness, they are acknowledgements of physics. The lakes have always operated within seasonal cycles, ice forms and breaks. Storms rise and dissipate, water levels fluctuate. Climate trends may alter patterns, but wind will still transfer energy to water, and cold will still extract heat from the human body. Respect means remaining attentive to those processes as they evolve. It also means understanding that risk cannot be eliminated entirely. Even experienced captains encounter unexpected mechanical failures. Even trained swimmers may misjudge currents. Even well-forecasted storms may intensify slightly beyond projection. Respect prepares for contingencies, carrying spare fuel, maintaining equipment rigorously, practicing man-overboard drills, knowing how to float rather than fight a rip current. The Great Lakes are not enemies to conquer, they are environments to navigate. Standing on a shoreline at dusk, watching light fade across open water, the surface may appear calm. That calm does not contradict the stories of storms or shipwrecks. It represents one state in a system capable of many. Respect recognizes that transition between states can occur quickly. It removes the illusion that calm guarantees continuation of calm. It replaces assumption with observation. People who live along these shores often speak of the lakes with affection. They fish, sail, swim, and walk beaches year after year. Their familiarity does not erase caution. It deepens it. Children raised near the lakes are often taught early to check flags before swimming, to wear life jackets without argument, to watch wind direction. This cultural knowledge accumulates quietly. The goal is not to instill anxiety. It is to align perception with reality. When perception matches reality, fear becomes unnecessary. You do not fear gravity when walking downstairs. You respect it by holding the railing and watching your step. The Great Lakes operate on principles just as consistent. Wind, depth, cold, current, ice. Recognizing those elements transforms the lakes from mysterious hazards into powerful systems that can be understood and navigated responsibly. And in that understanding, the shoreline becomes neither falsely safe nor inherently threatening, simply the edge of a vast freshwater system that has shaped history, demanded skill, and offered remarkable beauty for thousands of years, continuing to do so with the same steady indifference to whether we approach it with assumption or with awareness. Stand at the edge of Lake Superior at dusk or Lake Michigan at sunrise, and the surface looks timeless. Waves move in, waves move out, wind passes, light shifts, the horizon holds steady. It is easy to believe that the lake exists only in the present moment. But the water holds memory, not memory in a conscious sense, not stories whispered beneath the surface. The memory is physical, layered, stored in temperature, in sediment, in preserved wood resting on the lakebed. The Great Lakes remember glaciers. Their basins were carved by ice thousands of feet thick. That ice pressed the Earth's crust downward, scraped valleys deeper, shaped shorelines that still determine how waves refract today. Every storm that builds across Lake Michigan does so within a basin sculpted during the last ice age. The water remembers wind patterns. Season after season, prevailing winds shape sandbars. They carve bluffs. They transport sediment along shore. A beach that exists today may have looked different 50 years ago. It may look different 50 years from now. That change is not random. It reflects accumulated interaction between wind and water. The lakes remember cold. Deep water layers retain winter long after surface warmth returns. Even in August, far below the surface, temperatures hover near what they were in March. This thermal memory influences storm intensity in autumn. It determines how quickly hypothermia develops. It shapes ecosystem cycles. The lakes remember ships. Steel hulls and wooden schooners rest intact in dark depths. Their outlines remain sharp because cold fresh water slows decay. Names painted decades ago are still legible in places. Those wrecks are not symbolic memory. They are physical records of moments when wind, wave, and human judgment intersected. The lakes remember ice. Pressure ridges form and collapse. Ice sheets drift and fracture. Shorelines bear marks of winter shoves. Even when summer returns, the erosion patterns shaped by moving ice remain visible. Each season leaves imprint. High water years carve new edges along bluffs. Low water years expose rocks and shoals. Storm surges rearrange sandbars overnight. The lake adjusts incrementally, never entirely fixed. Climate trends add another layer of memory. Warmer years shift ice cover duration. Stronger rainfall events alter runoff patterns. Data collected from buoys and satellites records these shifts. Temperature profiles plotted over decades show gradual change. The lakes respond slowly, but they respond. The water remembers everything through consequence. Nothing disappears without effect. A storm that erodes a shoreline leaves sediment suspended, then deposited elsewhere. A sunken vessel becomes habitat. A year of heavy rainfall raises levels that influence infrastructure planning for the next decade. The memory is cumulative, and people remember too. Communities along the Great Lakes pass down stories of November gales. Families recall relatives lost at sea. Lifeguards remember rescue attempts shaped by rip currents that formed in specific weather patterns. Education grows from these experiences. Children are taught to float rather than fight a current. Boaters learn to check marine forecasts instead of relying on shoreline appearance. Anglers measure ice thickness rather than assuming strength. The water does not change its rules. Wind transfers energy. Cold extracts heat. Depth stores temperature. Ice moves under pressure. Currents follow contour. The memory lies in how these rules have played out repeatedly over time. When you look across the horizon on a calm day, it may feel as though the lake has forgotten its storms, but the structure beneath the surface remains. The depth carved by glaciers still holds cold. The sandbars shaped by last year's storm still influence this year's rip currents. The breakwalls built after previous surges still stand against new waves. Memory does not require consciousness. It requires continuity. The Great Lakes have existed in their current form for roughly 10,000 years. In geological terms, that is recent. In human terms, it is vast. Across that span, the lakes have absorbed heat, released storms, frozen, thawed, risen, fallen. They have preserved what sank into them. They have reshaped their edges gradually and sometimes abruptly. Standing at the shoreline, it is tempting to see only surface. Light reflecting off small waves, children running along sand, a freighter moving steadily across distant water. But beneath that surface lies accumulated consequence. Respect grows naturally from recognizing that continuity. The lake you see today is not separate from what it was yesterday. Conditions now reflect what wind did hours ago, what temperature did months ago, what ice did last winter. Understanding this continuity shifts perspective. You no longer interpret calm as permanence. You see it as a phase within a larger cycle. You no longer assume proximity to shore guarantees safety. You recognize that energy concentrates there. You no longer treat fresh water as inherently gentler than salt water. You understand that wave period and fetch matter more than salinity. The water remembers, and so should we. Not with fear, not with hesitation that prevents engagement, with awareness. When you check the forecast before launching, you acknowledge past storms. When you wear a life jacket in early spring, you acknowledge cold stored at depth. When you swim parallel to shore to escape a current, you apply knowledge earned over decades of observation. The horizon remains straight. The waves continue their rhythm. Storms will rise again in November. Ice will form along edges in January. Fog will drift across open water in July. The lakes will not announce their shifts dramatically every time. They will simply continue operating according to forces that have shaped them since glaciers withdrew. And standing at the water's edge, knowing all of this, the surface looks different. Not less beautiful, not less inviting, just more complete. Because beneath the reflection of sky lies depth, current, cold, wind history, preserved steel, layered sediment, and the accumulated physics of thousands of seasons. The Great Lakes are not dangerous because they are malicious. They are dangerous when we forget what they remember. And when we remember alongside them, when we align expectation with scale, temperature and motion, the shoreline becomes not a place of false comfort or exaggerated fear, but the meeting point between human intention and a vast freshwater system that has always been exactly what it is,